When astronomers first detected an object on a path that clearly originated beyond our solar system in 2017, the world was captivated. That object, called Oumuamua, became a source of endless speculation and debate. A slender, tumbling visitor that refused to behave like anything seen before. Now, years later, a new interstellar traveler has entered the stage, 3I Atlas. This third known interstellar object, following Oumuamua and 2I/Borisov, is already reshaping how scientists think about the traffic between the stars. Discovered by the Atlas survey, 3I Atlas represents a crucial opportunity to observe an interstellar body with the full suite of modern astronomical tools, allowing humanity to peer deeper into the mechanics and chemistry of other star systems than ever before. Before we start, hit the like and subscribe buttons for more updates. The excitement surrounding 3I Atlas stems from both its timing and its characteristics. Detected while it was still inbound toward the inner solar system, the object provided astronomers with precious lead time to prepare telescopes for detailed observation. Unlike the case with Oumuamua, which was only spotted after it had already passed perihelion and was racing away, 3I Atlas was found early enough to allow for comprehensive study. This advance notice means the world's observatories, both on the ground and in space, could coordinate to track its composition, behavior, and trajectory. For planetary scientists, it felt like finally getting a second chance at a cosmic encounter that had once slipped through humanity's grasp. From the moment of its discovery, 3I Atlas displayed features that set it apart. Preliminary orbital analyses confirmed its hyperbolic trajectory. Its speed was simply too high to be bound by the sun's gravity, ensuring it was an interstellar interloper. Its motion suggested it entered the solar system from a direction near the constellation Lyra, though, as with all such detections, the precise origin within the Milky Way remains uncertain. The key fact was undeniable. This was matter from another star system, moving freely through interstellar space before brushing past ours. That realization alone carries profound implications for understanding how material migrates between stars and what it might carry with it. The brightness curve of 3I Atlas indicated a roughly spherical or mildly elongated shape, a striking contrast to the pancake-like or cigar-shaped silhouette inferred for Oumuamua. This difference suggested that interstellar visitors come in many forms, shaped by diverse histories. Spectroscopic observations quickly became a priority. Early readings hinted at volatile materials, possibly water ice and carbon-based compounds, sublimating as it approached the sun. That behavior immediately distinguished it from Oumuamua, which exhibited no visible coma despite subtle non-gravitational acceleration. Instead, 3I Atlas seemed more akin to a comet, its surface reacting dynamically to solar radiation and heat. If Oumuamua was enigmatic because it didn't behave like a comet, 3I Atlas fascinated scientists because it did, but in a distinctly alien way. Its spectrum carried signatures that did not perfectly match known solar system comets, suggesting subtle differences in composition. Perhaps it formed around a cooler star, or within a protoplanetary disk rich in exotic carbon compounds or nitrogen ices. Each data point teased out clues about its birthplace, as if its minerals and volatiles were the fossilized record of another planetary nursery. In essence, 3I Atlas became a messenger from an unseen world, carrying with it the story of its home system. The ability to study an interstellar object with this level of detail represents a major milestone in planetary science. For decades, theories about planet formation were based solely on observations within the solar system and on remote sensing of exoplanets. But an interstellar object is tangible evidence, matter that once belonged elsewhere, now passing through our neighborhood. By comparing the isotopic ratios, molecular structures, and spectral features of 3I Atlas to those of comets and asteroids native to the Sun's realm, scientists can begin to chart how unique or universal the chemistry of planetary formation really is. It offers a chance to test whether our solar system's recipe for planets and organic molecules is common across the galaxy or a local anomaly. As observations deepened, models of the object's structure began to take shape. Data from infrared instruments hinted at a dusty mantle overlaying icy layers, perhaps the remnant of long exposure to cosmic rays during its voyage through interstellar space. over millions or even billions of years. That bombardment would have altered its surface, darkening and hardening it into a protective shell. Beneath that crust, frozen volatiles could have remained preserved since the object's formation. When solar radiation finally reached it, the ice would have begun to sublimate, creating a faint but measurable outflow of gas and dust. This process not only confirmed the object's active nature, but also provided a natural laboratory for studying how interstellar bodies weather the extremes of deep space. Another revelation came from its rotation and light curve behavior. 3I Atlas spun at a moderate rate, with slight irregularities that suggested a complex internal structure or past collisional history. Unlike Oumuamua's chaotic tumble, its motion appeared relatively stable, implying that it had not undergone the same violent ejection process. This stability could mean that 3I Atlas originated from a more quiescent environment, perhaps gently displaced from its home system by gravitational perturbations rather than catastrophic planetary disruption. Each aspect of its motion told a part of its story, a story written across cosmic distances. One of the most tantalizing scientific opportunities came from studying the isotopic fingerprints within its material. Spectroscopy at high resolution hinted at ratios of carbon, oxygen, and nitrogen isotopes that diverged slightly from those found in typical solar system bodies. Such differences, though subtle, carry enormous implications. They suggest that the molecular clouds and protoplanetary disks across the galaxy produce matter under a broad range of conditions. Understanding those variations could shed light on the diversity of planetary systems and on the ingredients available for life. If the chemistry of 3I Atlas reflects a different balance of organic precursors, then it also reflects the possibility that life's raw materials may be distributed more unevenly or more generously throughout the cosmos than previously thought. Beyond its composition, 3I Atlas reinvigorated the debate about how interstellar objects are launched in the first place. In one prevailing theory, gravitational interactions with giant planets fling leftover debris from the planet-forming process out of their systems at escape velocity. Another theory suggests that close encounters between stars, especially in young clusters, can expel material en masse. 3I Atlas may provide clues to which scenario dominates. Its composition and physical integrity imply that it survived ejection without total fragmentation, indicating that gentle gravitational nudges may have been sufficient. In that sense, it could be representative of the quiet exodus of material that occurs naturally as planetary systems mature. The broader implications of 3I Atlas extend beyond astronomy into philosophy and the ongoing search for life. Each interstellar visitor serves as a tangible link between distant worlds. Long before humanity possesses the technology to travel to other stars, these small emissaries come to us, carrying the cosmic dust of alien suns. If such objects are common, and models increasingly suggest that they are, then the exchange of material between systems may be a fundamental feature of the galaxy. It implies that molecules, minerals, and possibly even prebiotic compounds could wander freely among the stars, seeding young planetary systems with new ingredients. This natural mixing could play a crucial role in spreading the building blocks of life throughout the Milky Way. The timing of the discovery also highlighted the growing maturity of astronomical surveys. The Atlas system, designed primarily to detect potentially hazardous near-Earth asteroids, proved once again how powerful wide-field sky monitoring can be. With automated telescopes scanning vast sections of the sky every night, the chances of detecting faint, fast-moving interstellar objects are improving dramatically. The detection of 3I Atlas demonstrates that humanity has entered an era where such discoveries may become routine rather than extraordinary. Each new detection will refine our understanding of the population of interstellar wanderers and how they interact with the solar system. As telescopes around the world turn toward 3I Atlas, the observations spanned the entire electromagnetic spectrum. Optical data provided insights into its surface color and albedo, revealing a reddish hue likely caused by space weathering. Infrared observations probed its temperature and volatile content. Radio telescopes searched for outgassing signatures, while ultraviolet sensors looked for ionized emissions. Even neutrino and cosmic ray observatories took note, just in case the interaction between solar radiation and the object's materials produced any detectable anomalies. The coordination of so many instruments represented one of the most comprehensive observation campaigns in recent history, a testament to how deeply the astronomical community had learned from the fleeting case of Oumuamua. Among the most exciting possibilities raised by 3I Atlas was the potential for direct sampling, though still beyond immediate reach. Space agencies began discussing hypothetical mission designs that could intercept future interstellar objects. If 3I Atlas had been discovered just a few months earlier, a fast response probe might have been feasible. That realization is driving a new era of mission planning where modular spacecraft could be launched on standby, waiting to chase down the next interstellar visitor. The dream of touching material from another star is no longer science fiction, but a concrete engineering challenge within the next few decades. On a more conceptual level, 3I Atlas has redefined what it means for a solar system to be an open system. The discovery supports the idea that interstellar exchange is not rare or accidental, but a continuous, low-level process. The solar system, like others, constantly loses and gains material through gravitational interactions and random collisions. Over cosmic timescales, this exchange could blend the dust and debris of countless stars into a shared galactic heritage. Every rock and grain of dust within our planetary system might contain atoms that once belonged to another world. The arrival of 3I Atlas makes that cosmic interconnectedness vividly real. As observations continued, astronomers refined its size and mass estimates. Based on its brightness and assumed reflectivity, 3I Atlas likely measured between 100 and 400 meters in diameter, comparable to or slightly larger than Oumuamua. Its density in response to solar heating hinted at a mixed composition, part icy, part rocky. That blend suggests it may have formed in the outer regions of its home system, where water and volatiles condense, but where solid silicates still play a structural role. Such regions are analogs to the Kuiper Belt in our own system, cold, distant zones filled with primordial remnants from the time of planet formation. In that sense, 3I Atlas might represent the archetype of what many interstellar objects will turn out to be, fragments from the frozen outskirts of alien planetary disks, flung into the void when their systems undergo gravitational reshuffling. The study of 3I Atlas also provided a powerful calibration for our models of how light interacts with interstellar debris. Its photometric behavior helped refine estimates of how cosmic rays darken surfaces over time and how volatiles escape when exposed to stellar heat. That data, in turn, feeds into simulations of how many such objects should be detectable by future observatories. The Vera Rubin Observatory, when fully operational, is expected to uncover dozens of interstellar visitors every decade. 3I Atlas, therefore, stands as both a scientific discovery and a harbinger of what's to come, a sign that the galaxy is alive with movement and exchange. The object's trajectory through the solar system also offered a rare opportunity to test gravitational models and the influence of radiation pressure. Tracking its path with exquisite precision allowed researchers to measure tiny deviations from Newtonian predictions caused by outgassing or solar photon momentum. Such measurements contribute to a broader understanding of how small bodies move and evolve under the combined forces of gravity, radiation, and their own internal processes. In doing so, 3I Atlas served as a natural probe of both celestial mechanics and the subtle physics governing interplanetary motion. Culturally, the appearance of 3I Atlas rekindled public fascination with interstellar space. The discovery captured imaginations not because it promised answers, but because it embodied questions. What worlds lay in the direction it came from? How many such travelers have passed unseen through the solar system across the ages? Could Earth itself be peppered with microscopic debris from other stars, unnoticed until now? These questions bridge the gap between science and wonder, reminding humanity that exploration begins not with certainty, but with curiosity. While Oumuamua ignited speculation about artificial origins due to its unexplained acceleration, 3I Atlas brought a welcome grounding in natural science. Its behavior, while unusual, fit within known physical processes. Yet even so, it stretched those processes to new extremes, challenging assumptions about what comets and asteroids can be. By existing at the boundary of known categories, it forced astronomers to expand their definitions, to reconsider how materials behave under alien conditions. This continual reshaping of knowledge is one of the hallmarks of astronomy. where each discovery simultaneously answers old questions and generates new ones. The color of 3I Atlas, deep red with subtle blue undertones in infrared, told another part of its story. Such hues often result from tholins, complex organic compounds formed by radiation acting on simple ices. If confirmed, their presence would indicate that organic chemistry operates widely across the galaxy, independent of any biological processes. It would mean that the same molecular precursors that shaped early Earth and paved the way for life might be forming everywhere. Each interstellar comet becomes a drifting seed of potential, carrying organic material from one system to another like cosmic pollen. Observations from space-based instruments such as the James Webb Space Telescope added an unprecedented level of detail. Webb's sensitive infrared detectors identified spectral features consistent with frozen carbon dioxide, methane, and perhaps even ammonia. These findings implied that 3I Atlas formed in an environment colder than most regions of the early solar nebula, perhaps near the outer fringes of its native system. Such chemistry hints at a sun smaller and dimmer than ours, or at a planet-forming disk that extended farther into frigid space. Through that lens, 3I Atlas became not just an object of study, but a distant geological sample, a piece of another solar system's architecture delivered directly to us. In parallel, computer models attempted to trace the object's origin by projecting its trajectory backward through galactic coordinates. While the uncertainty grew rapidly due to gravitational interactions and the sun's motion, the simulation suggested it may have originated from a region of the galaxy rich in young stars. If so, 3I Atlas might be a refugee from a system that formed within the past few 100 million years, ejected before its planets fully coalesced. That possibility adds another layer of intrigue. We may be witnessing material from the early stages of another solar system's evolution, still carrying the fingerprints of its creation. The interstellar nature of 3I Atlas also allows scientists to test theories about cosmic ray exposure. By analyzing how its surface reflects light across wavelengths, researchers can estimate how long it has drifted between the stars. The pattern of radiation-induced damage provides a kind of cosmic clock. Initial estimates suggested that 3I Atlas has been wandering the galaxy for tens of millions of years, possibly longer. During that time, it would have crossed the interstellar medium, endured collisions with microscopic dust, and absorbed the faint starlight of countless suns. Its survival through all that testifies to the resilience of solid bodies and the stability of material ejected from planetary systems. As the object approached perihelion, its activity peaked. Jets of sublimating gas produced a thin asymmetric coma, faintly visible even in amateur telescopes. The morphology of that outflow, directional rather than diffuse, implied that sublimation was localized to specific regions, perhaps where the insulating crust had cracked. This pattern provided direct insight into the internal structure and thermal dynamics of interstellar bodies. The gases escaping from those jets carried trace compounds that could be analyzed spectroscopically, offering a chemical fingerprint of the subsurface materials. Each observation tightened the link between 3I Atlas and the broader story of how planetary systems expel and evolve material. Even as the object began its outbound journey, fading from sight, it left behind a treasure trove of data. Thousands of images, spectra, and measurements from around the world now form a reference dataset for future interstellar detections. By comparing those records with new discoveries, astronomers can identify patterns, recurring spectral lines, typical velocities, characteristic shapes that define a new class of objects. In this way, 3I Atlas will serve as a benchmark, a touchstone for the emerging field of interstellar planetary science. The appearance of 3I Atlas also underscores a deeper truth about the galaxy's dynamism. Planetary systems are not isolated islands, but participants in a grand cosmic circulation. Debris ejected from one system may seed another, blurring the boundaries between ours and theirs. The atoms in Earth's oceans, the dust in comets, and the elements in interstellar visitors like 3I Atlas may share common ancestry from long-dead stars. Each new interstellar object, therefore, becomes a reminder of our shared cosmic origin, a reaffirmation that the universe is less a collection of separate worlds and more a continuous ecosystem of matter and energy. From a technological perspective, The discovery of 3I Atlas represents a triumph of vigilance and preparedness. Automated surveys, machine learning algorithms, and global coordination between observatories made it possible to detect and characterize an object traveling at tens of kilometers per second across vast distances. It showcased how far observational astronomy has come in just a few decades. Where once such an object might have passed unnoticed, now it becomes the focus of worldwide study. This capacity marks the transition of humanity from passive observers of celestial events to active participants in galactic discovery. The legacy of 3I Atlas will likely be measured in how it reshapes priorities for exploration. Plans for rapid response missions, specialized telescopes designed to spot faint fast movers, and networks of amateur astronomers contributing to global tracking efforts all draw inspiration from its passage. Each improvement increases the odds that the next interstellar visitor will be met not just with observation, but with direct engagement. The dream of catching one, studying it up close, and perhaps even returning a sample to Earth now feels tangible. When that happens, humanity will hold in its hands the dust of another sun, a physical link across light years. As 3I Atlas continued its silent glide through the solar system, the deeper implications of its presence began to unfold. Every layer of observation, every photon captured by a telescope, peeled back another curtain between humanity and the grand processes that shape the galaxy. It was not simply a comet or an asteroid from afar. It was a direct thread to the mechanisms of creation and destruction that govern all planetary systems. Scientists realized that by studying this object, they were not just learning about one traveler, but about the entire network of stellar systems that populate the Milky Way, connected invisibly through the shared traffic of interstellar debris. The journey of 3I Atlas had begun billions of years ago, perhaps in the aftermath of planet formation around a distant sun, and now its long exile through the interstellar void had brought it into our light. There was something profoundly humbling about tracing its path. The fact that it had crossed light years of emptiness, buffeted by cosmic radiation and the faint gravitational whispers of passing stars, only to enter the narrow window of detectability within the human lifespan seemed almost poetic. For countless millennia, it had traveled unseen, its trajectory determined long before the rise of humanity, before even the birth of the solar system as we know it. In that sense, 3I Atlas became a reminder of how small and transient our perspective truly is. Its brief visibility, just months or perhaps a few years, represented a mere heartbeat in its cosmic journey. Yet within that fleeting moment, human instruments managed to capture its image, measure its spectrum, and decipher pieces of its story. It was a meeting across time and distance, an intersection between two vastly different scales of existence. One of the subtler revelations from its study came from the way sunlight interacted with its surface. The reflected spectrum indicated complex layers of material, organics, silicates, and possibly metal-rich inclusions, all suggesting a long geological evolution. Some researchers proposed that it might once have been part of a larger body, perhaps a fragment from a shattered moon or planetesimal. The collision that freed it from its parent system could have been gentle enough to preserve its internal structure, but forceful enough to push it onto a hyperbolic trajectory. Over eons, the object would have been sculpted by cosmic erosion, its once pristine ice darkened by radiation, its minerals chemically altered into resilient compounds. The end result was a relic of another world, reshaped into something new by the interstellar environment. When sunlight began to warm its surface, the chemistry of that long dormancy awakened. Jets of vaporized material escaped from beneath its crust, carrying dust and volatile molecules into a thin envelope around it. Through spectroscopy, astronomers detected faint emissions consistent with carbon monoxide and possibly acetylene, molecules not uncommon in solar system comets, but in slightly different proportions. Those differences were enough to suggest that 3I Atlas had formed in a nebula with a distinct temperature profile and chemical mix. That detail, seemingly small, opened a doorway into the diversity of planetary birthplaces across the galaxy. If the molecular ratios of interstellar visitors differ systematically from those found in our system, scientists could one day map the galactic distribution of chemical environments the way geologists map rock strata on Earth. What made 3I Atlas especially significant was that it allowed direct observation of how interstellar ices behave when exposed to sunlight after millions of years in darkness. The outgassing rates, the distribution of dust particles, the changes in reflectivity, all these phenomena provided clues about how material evolves between the stars. It confirmed that the interstellar medium is not a dead zone, but a dynamic arena of transformation. Even in the coldest regions, chemical reactions occur slowly but steadily, creating new compounds from cosmic radiation and microscopic collisions. These processes may seem glacial by human standards, but over geological timescales, they can reshape entire surfaces and alter the composition of matter traveling through space. In this sense, 3I Atlas acted like a probe of interstellar chemistry, revealing how raw materials age and transform during their endless drift. As 3I Atlas neared the Sun, scientists watched its activity grow more intense. Small bursts of gas ejected particles into curved tails that followed solar radiation pressure. Unlike the familiar tails of comets from the Oort cloud, these emissions exhibited irregular flickers, as if driven by deep, uneven pockets of trapped volatiles. The pattern hinted at a surface that was not homogeneous but patchy, with layers of different composition and density. That complexity mirrored the chaotic conditions of planet formation, regions where materials of varying volatility mixed and froze at different distances from the central star. In analyzing those patterns, researchers found hints of the object's thermal history, perhaps even clues about the radiation flux of its parent system. Every burst of gas was like a signature, revealing a memory of the temperature, composition, and dynamical conditions of a distant birthplace. The reaction of the scientific community to these findings was one of cautious awe. Decades ago, the very idea of interstellar debris crossing into the solar system had seemed theoretical. Now, with multiple confirmed cases, it was evident that the galaxy is far more interconnected than once believed. The density of such objects in interstellar space may be higher than early models predicted. Some estimates suggest that at any given moment, thousands of them are passing through the outer reaches of the solar system, undetected by current technology. The discovery of 3I Atlas thus served as both a revelation and a challenge. A revelation of the galaxy's ceaseless exchange of matter, and a challenge to build instruments sensitive enough to capture more of these fleeting visitors. In reflecting on its passage, astrophysicists began revising models of how planetary systems eject material. For every planet that forms, countless smaller bodies are cast out by gravitational interactions. Over time, these remnants populate the interstellar void, drifting until captured temporarily by another star's gravity, or until they disintegrate through collision or radiation. The galaxy, then, is not a static collection of isolated systems, but a vast, evolving ecosystem where material is constantly recycled. 3I Atlas embodied that idea perfectly. It was both a survivor of its own world's formation and a participant in a broader galactic cycle. The same processes that once expelled it may also shape the boundaries of countless other systems, redistributing the raw ingredients for future planets. The subtle interplay between light and matter that defined the appearance of 3I Atlas held deeper implications. By studying its photometric variability, astronomers inferred how sunlight was absorbed and re-emitted across its surface. That, in turn, revealed information about the size and texture of its dust grains, about the porosity of its crust, and about how heat traveled through its interior. Each of these physical characteristics helped refine models of how small bodies evolve in extreme environments. For instance, the delayed response of its outgassing to sunlight suggested a layer of insulating material only a few centimeters thick, a thin skin that preserved the frozen core beneath. That insight is crucial not only for understanding interstellar objects, but also for designing spacecraft missions that might one day interact with them. Understanding their structure means predicting how they might behave when approached, drilled, or impacted by probes. The story of 3I Atlas also served as a bridge between astrophysics and the study of origins. The detection of organic molecules on its surface raised questions about the distribution of life's precursors across the galaxy. Complex carbon chains, possibly formed through long-term exposure to ultraviolet radiation, coated its exterior. If such molecules are widespread on interstellar objects, it strengthens the argument that prebiotic chemistry is a galactic phenomenon rather than a planetary accident. Some scientists even speculated that bodies like 3I Atlas could play a role in panspermia, the theoretical transfer of life or its building blocks between star systems. While there is no evidence that any biological material survived its ejection and journey, the concept resonates with the recognition that chemistry itself is mobile, capable of crossing light years and carrying potential wherever it goes. The object also sparked renewed discussions about the architecture of other planetary systems. Its composition suggested that even modest-sized stars can produce icy bodies similar to our comets. That supports the idea that debris disks, once thought to be rare, may be a near-universal stage in planetary evolution. If nearly every system produces objects capable of being ejected, then the galaxy must be filled with such travelers, invisible most of the time but collectively forming a vast migratory population. 3I Atlas thus represents a data point in a much larger pattern, one that reveals how stars not only give birth to planets, but also continuously shed material into the galactic medium. As scientists tracked 3I Atlas outbound, the diminishing signal forced increasingly creative approaches to analysis. Observatories combined data across wavelengths to extract faint details from the noise. Each observation became a race against time as the object dimmed and the distance increased. Yet, even as it faded, the data it had provided continued to yield insights. Sophisticated models reconstructed its probable internal composition, while laboratory experiments attempted to replicate its behavior under simulated solar heating. The synergy between observation and experiment created a feedback loop of discovery, each hypothesis tested against the reality of this single fleeting visitor. The philosophical resonance of 3I Atlas cannot be overstated. Its existence reminds humanity that the universe is a continuum, not a collection of separate realms. Matter flows from one system to another, carrying history in its atoms. The very materials that make up our planet, carbon, oxygen, silicon, iron, were once forged in ancient stars and scattered across space before coalescing again into new worlds. 3I Atlas is a visible manifestation of that cycle, a piece of another world making a temporary crossing into ours. It symbolizes both impermanence and connection, the idea that even across light years the story of creation is shared. The object's endurance through interstellar space also challenged previous assumptions about how long small bodies can survive the rigors of cosmic radiation. Some models had predicted that ices would sublimate or erode completely after millions of years of exposure. Yet 3I Atlas arrived largely intact. That resilience suggests that many more such objects could endure over galactic timescales, potentially carrying stable materials for billions of years. It also raises intriguing questions about the preservation of molecular information. If complex organics can persist across those timescales, they might serve as a molecular record of chemical evolution in different regions of the galaxy. As it receded into the outer solar system, faint and slowing in brightness, 3I Atlas remained a focus of study through long exposure imaging. The dust and gas it left behind formed an ephemeral trail, a luminous memory slowly dispersing into the void. This diffuse residue became a temporary laboratory for studying how sunlight and solar wind interact with interstellar material. Tiny dust grains, each a fragment of an alien world, drifted outward, joining the endless stream of particles that fill interplanetary space. In a symbolic sense, the object had given something to the solar system, a scattering of atoms that would now orbit our sun for a time before drifting away again. Its detection also reshaped the strategies used to watch the sky. Astronomers began to refine algorithms to recognize the unique motion signatures of interstellar objects more quickly. Machine learning systems were trained on the data from 3I Atlas to improve pattern recognition for future discoveries. The goal was clear: to catch the next visitor earlier, while it was still approaching. The realization that these events could be frequent transformed them from rare curiosities into opportunities for ongoing study. In this way, 3I Atlas became a cornerstone of a new discipline, one that straddles planetary science, astrochemistry, and interstellar dynamics. The deeper scientists looked into its data, the more nuanced their understanding of galactic migration became. Even subtle details, like the exact ratio of isotopes in its gases, hinted at broader truths about the structure of the Milky Way. Some isotopic patterns matched predictions for material formed near the outer edges of spiral arms, where star formation occurs more sporadically. If correct, That would mean 3I Atlas originated in a quieter region of the galaxy, possibly far from dense stellar clusters. Its ejection might have been triggered not by planetary interaction, but by the slow tidal pull of passing stars. Such a scenario paints a picture of gentle exile rather than violent expulsion, adding emotional depth to its journey through the void. The process of interpreting its light curves also shed light on rotational evolution. Small torques from asymmetric outgassing subtly altered its spin rate over time, revealing how such forces can change an object's orientation during close passes near stars. This knowledge has applications far beyond 3I Atlas itself. It informs how we understand the long-term behavior of comets, asteroids, and even spacecraft. It demonstrated that even minor thermal effects can accumulate into significant dynamical consequences, shaping trajectories and lifespans in unexpected ways. Throughout the global observation campaign, collaboration reached unprecedented levels. Observatories in both hemispheres shared real-time data, combining optical, infrared, and radio results into a unified model. Students and professionals alike contributed analyses, and amateur astronomers captured images that helped refine positional data. This collective effort illustrated the democratization of modern astronomy, a field once limited to a few large institutions, now operating as a networked global enterprise. In many ways, 3I Atlas became a shared human project, uniting scientists and enthusiasts across continents in pursuit of understanding. The poetic irony was that the object itself had no knowledge of the attention it commanded. It continued on its course, indifferent to the eyes that watched it, a silent ambassador from a distant sun. That very indifference lent it a kind of dignity, a reminder that the cosmos is not concerned with observers, only with motion, energy, and time. Yet humanity's response to that indifference, to observe, to question, to seek meaning, defined the essence of scientific inquiry. The study of 3I Atlas was as much a reflection of human curiosity as it was a study of celestial mechanics. In the wake of its passage, the theoretical implications expanded into new realms. If objects like 3I Atlas are common, they might serve as a medium of material exchange that shapes the chemical evolution of the galaxy. Over billions of years, such traffic could homogenize certain elements, spreading specific compounds from one stellar neighborhood to another. This process would mean that the galaxy's chemistry is self-mixing, ensuring that no system remains entirely isolated. The atoms in our solar system could thus include contributions from dozens of ancestral stars, carried here by generations of wandering debris. 3I Atlas, in this sense, was both a messenger and a participant in the ongoing blending of galactic matter. The event also forced scientists to consider new categories of interstellar bodies. Until recently, objects in our solar system were classified as asteroids or comets, defined by their composition and behavior under sunlight. But interstellar objects blur those boundaries. 3I Atlas, though comet-like, displayed characteristics inconsistent with traditional models. It outgassed selectively, rotated irregularly, and maintained unexpected thermal stability. This complexity has led to discussions about establishing a new classification framework that accounts for interstellar origin, composition diversity, and unique dynamical signatures. The taxonomy of small bodies may soon expand to include these travelers as a distinct population, one that represents the galaxy's vast diversity. From a cosmic perspective, the encounter between humanity and 3I Atlas illustrates how discovery often arrives without warning. The universe offers moments of fleeting contact, brief alignments between observer and phenomenon, before returning to silence. Each event becomes a snapshot of cosmic time, captured only because technology and awareness happen to coincide. In that way, the study of 3I Atlas is as much about timing as about knowledge. The instruments that detected it, the algorithms that flagged its motion, and the scientists ready to act were all part of a delicate sequence that could have easily missed its arrival. That fragility underscores how discovery depends on readiness, the willingness to look and the capacity to see. While much of the attention focused on its scientific value, the emotional impact of its discovery resonated deeply. To many, it symbolized connection, a reminder that even across unimaginable distances, there are bridges of matter linking the stars. Poets and philosophers saw in it an allegory of wandering and return, of endurance and transformation. Artists painted its imagined surface, glowing faintly against the dark, while writers speculated about the stories it carried from its long voyage. In that sense, 3I Atlas transcended science. It became a mirror for the human experience, the desire to explore, to persist, to find meaning in vastness. The trajectory of 3I Atlas through the solar system also served as an informal test of gravitational modeling on interstellar scales. By precisely tracking its position relative to planetary perturbations, astronomers could measure minute deviations that revealed the cumulative effects of the sun's pull, planetary interactions, and radiation pressure. Those measurements refine the constants used in celestial mechanics, enhancing the accuracy of orbital predictions for future interstellar visitors. Every detail, each arcsecond of its motion, contributed to a growing archive of interstellar dynamics that will serve future generations of scientists. As its brightness waned, the scientific community began to transition from observation to interpretation. The mountain of collected data became the foundation for theoretical work, simulations, and comparative studies. Researchers built virtual models of the object, adjusting parameters until they matched observed behavior. Through these models, they could reconstruct not just its trajectory, but its life story, the ejection event, the long drift through interstellar space, and the final transient encounter with the sun. These reconstructions revealed how the physics of small bodies operates on scales far beyond the confines of our solar system, linking local phenomena to galactic dynamics. The more one considers 3I Atlas, the clearer it becomes that its story is one of persistence. Through collisions, radiation, and cold, it endured. It drifted through regions of space where the nearest star lay trillions of kilometers away, where temperatures hovered near absolute zero, and where a single photon might travel unimpeded for years. And yet, despite that desolation, it remained whole enough to reveal its nature when the sun's warmth touched it. That resilience reflects a fundamental truth about the universe. Matter seeks equilibrium but resists annihilation. And even in isolation, it carries the memory of its origins. Through the deepening shadows of space, 3I Atlas continued its long outward climb, a silent traveler now receding from the inner solar system's glare. Though it had already crossed the inner orbits and passed beyond the warmth that awakened its volatile heart, the object's story was still being written in the minds of those who studied it. In observatories that now tracked its dimming glow, there was a sense that humanity was following not just a physical object, but the trace of an ancient motion begun long before the sun ever existed. The realization that something so small could embody such vast scales of time and distance gave the event a mythic weight, a reminder that the universe's history is carried not only in the stars, but also in the smallest fragments drifting between them. Every faint photon recorded by telescopes told another chapter of its departure. The object's tail, faint and thread-like, gradually dissipated into interplanetary space, scattering particles across the path it had taken. Some of those grains would remain in orbit around the sun for centuries, drawn into slow spirals by gravity and the solar wind, becoming invisible additions to the zodiacal dust. In this quiet dispersal, 3I Atlas left behind a lingering trace of its existence, a ghostly extension of its visit that would persist long after it had faded from human eyes. Each particle, once frozen in the cold of interstellar darkness, now carried within it the signature of another system and would, in turn, become part of ours, a microscopic merging of histories at the atomic level. The precise geometry of its orbit continued to fascinate dynamicists, who analyzed its trajectory as if it were a key to the hidden architecture of interstellar motion. Its speed upon entry, the angle of approach, and its perihelion distance offered clues about the density and velocity distribution of small bodies drifting between stars. Simulations showed that interstellar space is not a void, but a kind of slow-moving current where billions of unseen fragments cross paths in a cosmic drift. Most of them will never come near a star, but a few, by pure coincidence, find themselves drawn toward the light of systems like ours. 3I Atlas was one such lucky wanderer. The patterns encoded in its path allowed astronomers to refine estimates of how often these visitors should appear and how they are likely distributed across the galaxy. The data revealed that these encounters might occur every few years, perhaps even more frequently. But most objects remain too faint or too fast to be noticed. The long exposure images of 3I Atlas taken during its outbound leg captured subtle color changes as it moved away from the sun. The once active surface began to cool, freezing residual gases back into crystalline form. The reflected sunlight grew redder, its spectrum shifting as frost redeposited across its crust. This transformation told a story of dormancy returning, a return to the slow equilibrium of interstellar existence. The object was, in a sense, going back to sleep after its brief encounter with warmth. For planetary scientists, this cycle mirrored the processes that shape all comets: awakening, outgassing, fading, and then slumber. Yet for an interstellar body, that sleep could last for eons. The next star it might encounter lay perhaps tens of thousands of years away, a faint beacon in its unending night. The long-term fate of 3I Atlas became a topic of speculation. Given its velocity relative to the Sun, it would eventually leave the solar system entirely, crossing the heliopause and entering the true interstellar medium. Beyond that boundary, it would once again drift in the tenuous plasma between stars, passing through magnetic fields, interstellar clouds, and regions rich in cosmic rays. Each environment would etch subtle changes into its surface, gradually layering it with a patina of galactic experience. Some researchers imagined it traveling for another billion years, long after humanity itself had vanished, still bearing the faint marks of its visit through our skies. To think that an artifact of another world could outlast every civilization on Earth imbued its presence with an almost sacred quality. The continued analysis of its spectral data brought further surprises. In the ultraviolet range, faint absorption features hinted at compounds not commonly found in solar system comets. The likely candidates were complex nitrogen-bearing molecules formed under conditions of extremely low temperature and high radiation. These compounds, known as nitriles and isonitriles, are precursors to amino acids and other prebiotic molecules. Their presence in 3I Atlas suggested that the chemical pathways leading toward the building blocks of life operate not only within planetary atmospheres, but also within the frigid realms of interstellar space. The realization that such molecules could survive ejection, travel across light years, and remain chemically stable until entering a new star system reinforced the notion that the universe itself is a continuous laboratory for organic synthesis. Meanwhile, the object's internal structure, inferred from its rotation and response to solar heating, revealed that it was neither monolithic nor completely porous. Instead, it appeared to possess a compact core surrounded by a less dense mantle. This kind of stratification implied that it had undergone partial differentiation, an internal sorting of materials driven by heat during its early history. Such differentiation suggests that it once existed in a warmer environment, possibly within a protoplanetary disk where radiative heating or short-lived radioactive isotopes caused melting and refreezing cycles. If true, then 3I Atlas was not merely a chunk of primordial ice, but a remnant of a once active world, perhaps the broken fragment of a larger body that formed near a star. That conclusion connected it more deeply to planetary evolution. The same processes that shaped our asteroids, comets, and dwarf planets had also operated around other suns. The differences were in degree, not in kind. 3I Atlas became a symbol of cosmic parallelism, the idea that nature repeats its creative patterns throughout the galaxy. The similarity of its physical behavior to known solar system objects, combined with its clear interstellar origin, supported the view that the rules governing planetary formation are universal. Whether orbiting a red dwarf or a yellow star like our Sun, the raw materials of planets follow the same choreography: condensation, accretion, heating, and ejection. Each system is a variation on a galactic theme. This insight reshaped how scientists thought about exoplanetary systems. If debris like 3I Atlas is common, then the material environment of planet formation is not isolated. The dust and rock of one system can seed another, mixing their evolutionary paths. This implies a kind of chemical continuity across the Milky Way, a slow but relentless blending of matter that ensures no system remains chemically unique. It is a reminder that when we look for habitable worlds, we are not searching for anomalies but for repetitions of a cosmic process that has occurred countless times. Every new discovery strengthens the sense that the galaxy is a single organism made of stars, planets, and the endless exchange of their fragments. Beyond the scientific revelations, The cultural resonance of 3I Atlas deepened as its story spread. Writers, musicians, and philosophers found in it a metaphor for displacement and persistence. It was a voyager between homes, a being without origin or destination, moving endlessly through silence. Some saw it as an embodiment of human curiosity, an unconscious mirror of our own longing to explore beyond our boundaries. The object's indifference to our gaze made it all the more compelling. It was a symbol of the universe's vastness and of our desire to find meaning within it. Artists depicted it as a solitary traveler illuminated by starlight, trailing a faint ribbon of dust, forever on its way to nowhere and everywhere. Within scientific circles, it inspired new ambitions. The concept of rapid response missions gained traction. Small spacecraft capable of launching on short notice to intercept interstellar objects. The lessons of 3I Atlas fueled proposals for modular probes with high acceleration capabilities, ready to pursue the next visitor. These plans, though technically challenging, reflected a growing recognition that interstellar objects represent irreplaceable opportunities. Unlike distant exoplanets, which can only be studied through indirect light, these travelers bring actual material from other systems within our reach. A sample return from such an object would provide direct evidence of how matter is assembled beyond our sun. The potential for future encounters became more real as detection technology advanced. Surveys predicted that dozens of interstellar bodies might pass within the orbit of Jupiter every decade, though most would remain too small or faint to detect. As telescopes improved, the boundaries of the possible expanded. The next discovery could come at any time, and 3I Atlas served as both a prototype and a warning. A prototype for how to respond, and a warning that such chances vanish quickly. Each new detection would demand immediate coordination between observatories, spacecraft designers, and computational modelers. The discovery of 3I Atlas was, in effect, a rehearsal for an era when humanity regularly studies the messengers of other worlds. Even as it faded into the deep, 3I Atlas continued to influence thinking about galactic evolution. The realization that countless such bodies are drifting between stars alters our understanding of the Milky Way's structure. Interstellar space is no longer viewed as empty, but as a slow river of migrating matter. Some researchers speculate that this movement contributes to the distribution of metals and volatiles throughout the galaxy. Over billions of years, debris from young systems might enrich older regions, ensuring that even stars born in relatively barren environments can access heavy elements. In this way, interstellar objects become agents of galactic ecology, maintaining chemical diversity and feeding the cycles of star and planet formation. The rotation of 3I Atlas, still observable in faint flickers of reflected light, also offered insights into its past. Small variations in brightness revealed that its rotation period was gradually changing. That alteration could be due to asymmetric outgassing earlier in its solar passage, a process that imparts slight thrusts as jets of vapor erupt unevenly from the surface. These minute forces, accumulated over days and weeks, subtly alter spin and trajectory. Such behavior, though well documented in solar system comets, takes on new significance in an interstellar object. It demonstrates that even in the vacuum of deep space, microphysical processes, heat transfer, molecular sublimation, radiation pressure, combine to shape the destiny of celestial bodies. The faint glow recorded by deep field cameras months after its closest approach continued to offer hints about its surface composition. A persistent halo of dust surrounded it longer than expected, suggesting that some materials continued to drift off even at great distance. That lingering activity may have been driven by trapped gases escaping through microfractures, a kind of slow exhalation after the intense heating near the sun. The pattern of release hinted at a layered structure in which different compounds sublimated at different rates. Such complexity challenges the notion of uniformity in interstellar ices and strengthens the case that these bodies are archives of diverse chemical zones within their home systems. Amid the technical papers and data analysis, the sense of wonder remained palpable. Each observation, no matter how precise or mathematical, carried a human undertone, a sense of awe at witnessing something not of this solar system, something utterly foreign yet familiar in its adherence to the same physical laws. The fact that human instruments bound to one small planet could capture light from a traveler born around another sun testified to the reach of collective curiosity. It was as if for a moment the universe acknowledged that curiosity by offering a tangible connection. The object's departure was followed with the same attentiveness given to its arrival. Astronomers continued to calculate its trajectory, projecting where it might be thousands or millions of years from now. These simulations suggested it would travel through the local interstellar cloud, eventually passing near other stars before fading into uncharted regions of space. The idea that its path could be mapped even across such immense spans of time speaks to the predictive power of celestial mechanics. Yet there was also an inherent melancholy in those calculations, a recognition that this was a goodbye of sorts, not just to an object but to a unique moment in cosmic history. The study of 3I Atlas also had implications for planetary defense. Understanding how interstellar objects move and react to sunlight helps refine detection algorithms for potential impactors. Although interstellar bodies move too fast to be gravitationally captured, their trajectories provide extreme test cases for the systems used to track near-Earth objects. Lessons learned from its observation improved the capacity to distinguish between natural celestial visitors and artificial debris. The clearer that distinction becomes, the better prepared humanity will be for unexpected intruders, whether from within or beyond the solar system. There was another layer of fascination in the question of its age. By analyzing its radiation exposure and the degradation of its surface materials, scientists could estimate how long it had wandered through interstellar space. The results pointed to a timescale of hundreds of millions of years, perhaps even longer. During that time, it would have crossed spiral arms, moved through interstellar clouds, and perhaps come near other planetary systems. Each encounter would have left faint imprints on its surface, invisible but real. A record of galactic history written in chemistry rather than language. In studying it, humanity was effectively reading a page torn from the archive of the galaxy itself. The object's resistance to fragmentation near perihelion also challenged earlier expectations. Many comets of similar size break apart under the stress of solar heating and gravitational tides, yet 3I Atlas remained intact. That structural integrity implies unusual cohesion, possibly due to its composition or internal strength. It may contain sintered ice, a form of ice whose crystals have welded together under pressure and radiation exposure. Such material is stronger than the fluffy mixtures seen in many comets and suggests that long exposure to cosmic rays can gradually reinforce a body's surface. This process may be common among interstellar debris, enabling them to survive journeys that would destroy weaker bodies. The broader scientific community began to incorporate the findings from 3I Atlas into models of star system evolution. Its chemistry, motion, and structure all contribute to a growing understanding of how material circulates within the galaxy. It serves as a reminder that the building blocks of worlds are not confined to their birthplaces. Instead, they migrate, mix, and eventually contribute to new generations of stars and planets. In this sense, the galaxy functions as a kind of living organism, its lifeblood composed of drifting rocks, dust, and ice. Each interstellar object is a heartbeat in that organism's endless rhythm. In classrooms and lectures, educators use 3I Atlas to illustrate the continuity of cosmic processes. Students studying planetary science or astrophysics could see in it a living example of theories once purely abstract. It transformed the idea of interstellar travel from a speculative concept into an observable reality. The fact that such a body could be detected, studied, and understood within the span of a human lifetime brought the vastness of space into tangible focus. For a generation raised on images of distant exoplanets, 3I Atlas provided something more immediate: the evidence that material from those worlds sometimes comes to us. Even among the general public, there was a growing awareness that interstellar visitors are not mere curiosities. They are connections, threads weaving between stars, binding systems together in a quiet exchange that predates life and will continue long after. The realization that such exchanges happen naturally evokes a new kind of cosmic kinship. When looking at the night sky, one can imagine not just light traveling from those stars, but matter as well. Tiny fragments on billion-year journeys that occasionally cross our path. 3I Atlas was one of those fragments, and its brief appearance was a reminder of that invisible commerce. Speculation about its home system remained an ongoing fascination, while pinpointing its exact origin was impossible. Dynamical models suggested possible source regions, perhaps a young system in the outer spiral arm, or a fading cluster where stellar interactions were frequent. Whatever the case, somewhere in the galaxy there may still orbit a star whose planets share the same elemental fingerprint as 3I Atlas. To imagine that distant twin world, bathed in a different sunlight, shaped by different winds, adds a dimension of narrative to the object's existence. It becomes not just a traveler, but a messenger carrying news of places we have never seen. In considering all that had been learned from this single visitor, scientists began to speculate about what might come next. If 3I Atlas represented a typical interstellar comet, then the galaxy is filled with untold billions of such travelers. Some may be rocky, some icy, others metallic. Some might be ancient remnants from the early galaxy, older than Earth itself. Each would tell a different story about its origin, about the conditions under which it formed and the journey it endured. The more we find, the clearer the mosaic of galactic evolution will become. As the data archives from 3I Atlas expanded, they became a benchmark for the study of extrasolar materials. Future missions may compare collected dust particles from deep space against its spectral signatures, searching for matches. Such cross-referencing could identify whether interstellar dust collected near Earth's orbit comes from similar bodies. If so, it would mean that interstellar material is not just passing through, but actively mixing with the solar system's own debris cloud. Over geological timescales, that mixing could subtly alter the composition of planets, moons, and even the primordial reservoirs of volatiles that feed atmospheres and oceans. The implications of that idea stretch into the philosophy of life itself. If interstellar exchange of matter is common, then life, once it arises anywhere, may find pathways, however improbable, to spread, not through purposeful travel, but through the slow diffusion of its chemical precursors. Each interstellar object becomes a potential vessel of complexity, carrying the potential for life from one corner of the galaxy to another. It may never deliver organisms directly, but it can deliver the seeds, the molecules that make life possible. 3I Atlas thus stands as a symbol of continuity between chemistry and biology, between the lifeless and the living, between one world and the next. As it moved further into the darkness, long past the reach of most instruments, 3I Atlas became a point of meditation as much as study. It reminded observers that the universe's stories are not told only in bright explosions or dramatic collisions, but also in the quiet passage of a single rock through sunlight. Its meaning lies in persistence, the long endurance of matter, the inevitability of motion, the endless circulation of creation. Somewhere in that endurance lies a lesson for all who watch the skies, that the universe is not something to conquer but something to listen to interpret through patience and reverence. Perhaps by the time 3I Atlas crosses into its next stellar neighborhood, the memory of its fleeting passage through the solar system will have long been folded into other human narratives, new discoveries, new generations of astronomers, new civilizations that no longer look up at the sky with the same questions. Yet, even as that future unfolds, the object itself will remain a witness moving between epochs, bearing the imprints of countless stellar migrations. The light that once revealed its shape to our instruments will have long dispersed, but the object will continue to drift, gathering a film of interstellar frost, a layer of cosmic dust, and more stories carved into its skin by radiation. Each collision with a microscopic particle will become another punctuation mark in its infinite sentence. The physical endurance of 3I Atlas speaks to the deep balance that governs celestial bodies. Despite the harshness of space, temperatures near absolute zero, pressure almost non-existent, a constant bombardment of high-energy particles, it remains whole. It endures not because of strength in the human sense, but because of equilibrium. Its internal bonds neither strain nor relax, and the energies that strike its surface dissipate across a vast, unhurried scale of time. In that endurance lies a kind of serenity. Matter that survives ejection from its home system, millions of years of isolation, and a close passage by a foreign star achieves a state beyond fragility. Its stability is its story. That persistence is possible even in the most hostile conditions imaginable. As it moves further outward, the sun's influence grows faint. The solar wind thins into a distant whisper. Beyond the heliopause, where interstellar plasma begins to dominate, the object will enter a region few human artifacts have reached. There, it will encounter the subtle drift of the local interstellar cloud, a vast sea of atoms, magnetic ripples, and slow currents that stretch across light years. Each molecule of hydrogen it meets may have been part of other stars, exploded in supernovae, or condensed into distant nebulae. In passing through that ocean, 3I Atlas continues a cycle of exchange that predates planets, a circulation of material that binds the galaxy into a single breathing system. For scientists, imagining that journey is an act of synthesis between data and wonder. The physical trajectory is well understood, a hyperbolic escape, an outbound velocity that ensures it will never return. But beyond the numbers lies the intangible aspect, the recognition that this small body will continue its silent motion through regions that humanity may never reach. It will become a messenger, not only between stars, but between eras of cosmic time. Long after the Milky Way has rotated on its axis and new generations of stars have been born, 3I Atlas may still persist, a solitary reminder of ancient systems. In this way, it participates in the long continuity of existence, in which even the smallest fragment carries the memory of the universe itself. What continues to intrigue those who study its evolution is how its exposure to new environments will transform it. The surface that faced the sun will darken again, but beneath that crust, reactions will continue at molecular levels. Cosmic rays, traveling near the speed of light, will penetrate meters deep, breaking chemical bonds and creating new ones. Over millions of years, the chemistry of 3I Atlas will slowly rewrite itself, converting simple molecules into more complex forms. This transformation is not biological but alchemical, matter reorganizing under the laws of energy and time. Such processes may create compounds that have never existed in any laboratory, unique products of isolation and endurance. One day, should another civilization encounter it, they might read its molecular signature the way geologists read strata in rock, seeing in it the record of countless eons. Back on Earth, even as the object fades from observation, the data it provided continues to inspire new models of cosmic circulation. Simulations suggest that the galaxy's population of free-floating debris is immense. For every star, there may be trillions of fragments like 3I Atlas moving independently through space. Their collective mass rivals that of entire stellar clusters. Some are remnants of destroyed planets, others frozen comets, and some possibly metallic shards from planetary cores. Together they form a diffuse, unseen network, a galactic diaspora of matter. The passage of 3I Atlas through the solar system is merely one visible thread in that vast fabric. Understanding such motion transforms the idea of a galaxy from a static disk of stars into a living system of migration and exchange. This perspective also reshapes how scientists think about the origins of planetary systems. Instead of forming in isolation, systems may constantly interact through this slow traffic of materials. Each passing body carries with it foreign isotopes, exotic molecules, and the fingerprints of distant chemistry. When captured or fragmented, they contribute new elements to their host systems. Over billions of years, this process ensures that no system remains chemically pure. Every planet, every moon, every comet becomes part of a cosmic melting pot. In this way, 3I Atlas is not just a visitor. It is a representative of that perpetual blending that makes the galaxy a continuum rather than a collection of separate worlds. From a physical standpoint, the temperature it now experiences beyond the outer planets falls near 3 degrees above absolute zero, the same temperature as the cosmic microwave background. Under such conditions, even motion itself feels like stillness. Any residual gases have refrozen, sealing fractures, binding dust grains, and hardening the surface into a glassy crust. Inside, however, faint heat remains trapped from its close solar passage. Over decades, that warmth will migrate outward, cracking some layers, perhaps releasing tiny jets invisible to distant observers. Even in the deep freeze, change continues at a glacial pace. The object is not inert. It is patient, responding to the universe on a scale beyond human perception. The continuing fascination with 3I Atlas has also influenced the way humanity imagines its own future among the stars. The idea that small, unpiloted objects can traverse interstellar distances invites reflection on our own potential journeys. If matter can survive such vast migrations naturally, then human-made probes, designed with foresight and durability, could one day do the same intentionally. The enduring presence of 3I Atlas among the stars becomes an analog for our ambitions to send forth instruments, messages, perhaps even descendants capable of enduring cosmic time. It embodies what interstellar travel might mean, not speed or conquest, but endurance and quiet continuity. As the decades pass and its signal weakens beyond the reach of even the most sensitive instruments, its trajectory will remain recorded in human archives. Future astronomers may revisit that data, recalculate its motion with new precision, or attempt to find where it might be centuries hence. Perhaps one day a passing spacecraft, far beyond Pluto, will detect its faint reflection, confirming that it still drifts outward on the predicted path. That confirmation would link generations of observers across time, proving that even as knowledge evolves, the laws of motion remain unbroken. The confidence that such laws hold everywhere and forever is part of what gives discoveries like 3I Atlas their quiet power. Beyond the reach of observation, its narrative enters the realm of imagination. One can envision it crossing vast regions of darkness, passing through clouds of interstellar dust illuminated by distant starlight, casting a faint shadow that no one will ever see. Occasionally, it might encounter a sparse cluster of atoms dense enough to erode its surface over millions of years, creating new microcraters. These tiny scars, invisible on any human timescale, accumulate like wrinkles on a face, marking the passage of inconceivable time. Each interaction, each cosmic collision, writes another invisible story onto its body. If by some coincidence it were ever to pass close to another star, the encounter would replay in miniature the event we witnessed. As it entered a new system, light from that sun would again warm its surface, perhaps awakening buried volatiles. A faint coma might bloom, painting another ephemeral tale. For distant observers of that system, it would appear as a strange alien comet entering from the dark, a mirror of what we saw. They too might turn their instruments toward it, measuring, wondering, deducing its foreign origin. Thus, 3I Atlas becomes part of a repeating pattern, the same object interpreted differently by different civilizations across time, linking them through shared curiosity. The possibility that multiple intelligences might one day observe the same traveler adds a poetic dimension to its existence. It transforms an object of rock and ice into a cosmic narrative thread. Each civilization that notices it becomes a participant in a story written across light years, connected not by communication, but by shared recognition of the same phenomenon. It is a form of dialogue mediated by matter, transcending time. If intelligent life is widespread, 3I Atlas may one day be known in more than one language, cataloged in multiple archives under different names, its orbit traced by minds that never meet yet look upon the same messenger. The study of such bodies also refines our understanding of cosmic chronology. By analyzing their composition and age, scientists can create a timeline of stellar evolution in different parts of the galaxy. The materials in 3I Atlas, its ratio of carbon to oxygen, the crystalline structure of its ices, the isotopic fingerprints of its metals, serve as timestamps of the conditions that prevailed in its birthplace. Together with future discoveries, these data points could one day form a galactic map, not of positions but of histories, when and where certain elements were synthesized, how they migrated, and how the galaxy evolved chemically through the ages. Each interstellar object is thus both a fragment of space and a fragment of time. As understanding deepens, the philosophical implications widen. 3I Atlas shows that the boundaries of systems are porous, that separation is an illusion sustained only by distance. The same principle may apply to all structures in the universe, from galaxies to atoms. What we perceive as individuality may be merely temporary arrangement. The object's passage through the solar system becomes an allegory for this fluidity. It crossed into our gravitational sphere, shared its light, and then departed. Yet during that intersection, the sun's gravity altered its path slightly, and in return, however minutely, it altered the sun's. The mutual influence is infinitesimal but real, a literal demonstration that nothing exists in isolation, that every encounter leaves a trace. Such insights feed into a broader reflection on human existence. Just as 3I Atlas carries traces of the stars it has passed, so too does humanity carry the imprints of cosmic history within its own atoms. The iron in our blood, the calcium in our bones, the carbon in our cells, all originated in stellar furnaces. When we study an interstellar visitor, we are, in a sense, studying ourselves in another form. The same processes that forged our bodies also forged the objects. It is made of the same cosmic ingredients, arranged differently by chance and time. That realization closes the gap between observer and observed. It turns scientific curiosity into a form of kinship. Even the smallest details of its structure hold meaning for those who contemplate its nature. The fractures on its surface, perhaps caused by sudden heating near the sun, resemble fault lines seen in icy moons. Beneath those cracks, layers of dust alternate with frozen volatiles, forming a geological record of its past. Some layers may date back to its formation, while others were created by repeated cycles of heating and cooling during earlier stellar encounters. If one could slice through the object, those strata would reveal the rhythms of its life. The intervals between suns, the lengths of darkness, the intensity of cosmic exposure. It is, in effect, a diary written in minerals and ice. Speculative models suggest that the internal cavities of such bodies might trap exotic particles or gases accumulated over eons. When exposed to heat, these could produce unique chemical reactions never seen in terrestrial environments. Studying such reactions, even indirectly through their spectral traces, expands the boundaries of known chemistry. It hints that the universe's chemical repertoire is far wider than what earthly laboratories can replicate. Somewhere within 3I Atlas, new molecular structures may exist, temporary, unstable, but nonetheless real, waiting to be discovered in future samples from other interstellar travelers. In the broader arc of cosmic evolution, the existence of 3I Atlas also demonstrates the efficiency with which nature recycles its material. Nothing in the universe truly vanishes, it only changes form. Stars consume hydrogen and exhale heavier elements. Planets form, collide, and disintegrate. Fragments like 3I Atlas drift through space, eventually captured by other systems, where they may become seeds for new planets. The cycle repeats endlessly. To watch this process in motion is to witness the universe's own form of renewal, a perpetual rebirth in which destruction and creation are inseparable. For the human imagination, the concept of an interstellar object wandering for billions of years resonates deeply. It embodies endurance beyond comprehension. It exists on a timescale that dwarfs civilizations, continents, even species. Compared to its journey, the rise and fall of empires, the formation of languages, the entire span of human history are momentary flashes. Yet we, in this brief window of awareness, manage to notice it. That coincidence, our capacity to glimpse a traveler from another system during our short tenure as observers, feels almost miraculous. It underscores the rarity of conscious perception within the vast indifference of space. As scientific study turns to other objects and new missions, 3I Atlas remains a quiet benchmark, a point of reference for everything that follows. Its data will be revisited whenever a new interstellar body is discovered, its spectra compared, its trajectory used as a template. In that way, it continues to participate in future discoveries, long after its image has vanished from telescopes. It is not merely a relic of observation, but a standard, a calibration of how to interpret the unknown. Its legacy grows not by being seen, but by informing how we see. In time, as humanity develops technologies capable of leaving the solar system, it is conceivable that one of those vessels might cross paths with 3I Atlas. The odds are astronomical, but not impossible. The encounter would be poetic, a meeting between a product of conscious design and a product of natural chance, both born from stars, both crossing the interstellar sea. If such a meeting were ever to occur, the analysis of its surface would confirm everything we have imagined, and perhaps reveal details that no remote observation could capture. That possibility gives meaning to the act of imagining itself. Yet perhaps the true significance of 3I Atlas lies not in what it reveals, but in what it suggests. It hints that the galaxy is not empty, but filled with movement, that connections exist even when unseen. It teaches that distance does not equate to isolation, and that time, though vast, is still part of a single continuum. Its existence affirms that the universe is self-communicating. Stars speak to stars through the language of matter, exchanging fragments the way living beings exchange breath. We too are part of that conversation. To study an interstellar object is to listen to the universe talking to itself. The imagination can follow it still, moving outward through the dim regions between constellations. Behind it, The faint glow of the sun becomes one star among billions, indistinguishable in the crowded galactic field. Ahead, endless darkness stretches until the next encounter. Perhaps it will pass near a dense molecular cloud, where starlight filters through thick dust, painting its surface with new chemical colors. Or perhaps it will drift for tens of millions of years before another gravitational field tugs at its path. Whatever happens, its journey continues, unbroken, unhurried, infinite. The echo of that journey remains on Earth, in the laboratories where its spectra are stored, in the algorithms refined to find the next one, in the imagination of those who look up at night and think of unseen travelers. It has changed how humanity perceives its place in the cosmos. The boundaries of here and elsewhere have softened. The stars no longer seem remote but connected through the silent trade of their debris. Each grain of dust, each speck of rock, each glint of ice drifting through the void is part of a shared heritage. Beyond the veil of the heliosphere, 3I Atlas entered a realm where the sun's breath could no longer reach. The particles of the solar wind that had shaped its brief luminous tail were now scattered far behind it, replaced by the chill hush of the galactic medium. Here only the faint whisper of charged particles from distant supernovae flowed around it, a steady, invisible river that would polish its surface for ages. It was a place of darkness so complete that even starlight came thin and delayed, a light that had crossed billions of kilometers only to brush faintly against an object smaller than a mountain. And yet this silence was not emptiness. It was the quiet pulse of the galaxy itself, vibrating through fields of magnetism, waves of radiation, and the dust of uncounted suns. Into this sea of infinitesimal forces, 3I Atlas sailed with no destination but continuity. The physics of its motion was pure simplicity, an arc through four-dimensional space-time defined only by mass, velocity, and gravity's faintest touch. But simplicity in the equations belied complexity in its essence. Inside that fragment of frozen rock, minerals lay layered like pages of a cosmic book. Each crystal had once been molten, cooled, and irradiated under different conditions, marking the passage of epochs as if a clock were built within its atoms. The isotope ratios held stories of ancient nucleosynthesis, of the dying stars that had cast the materials of its world into a disk of dust and gas long before our sun was born. The same oxygen that now drifts through Earth's atmosphere may once have shared a furnace with the atoms that compose this visitor. The line between ours and theirs dissolves when viewed through such timescales. The galaxy's chemistry is one unbroken chain of inheritance. As it glided beyond the planetary orbits, its residual heat continued to seep outward, diffusing slowly through its mantle. That faint warmth, perhaps only a few degrees above the background of space, moved like a final echo of its encounter with starlight. In the crevices, sublimated gases froze again into minute frost crystals, glinting when struck by cosmic rays. This process of refreezing produced microscopic stresses, tiny fissures that would open and heal over millions of years. The surface of 3I Atlas was no longer the same as it had been upon entry. It bore the scars of its visit, each crack a record of its brief exposure to the sun's furnace. Time would seal them eventually, but the evidence would persist deep within, preserved as stratified memory. Far behind, the solar system receded into invisibility, yet the object carried a trace of its passage and altered trajectory. The sun's pull had bent its path slightly, changing the angle of its outbound motion. This infinitesimal adjustment meant that its journey through the galaxy was now subtly different than it would have been, a faint deflection that would, over millions of years, translate into a new galactic course. Such exchanges illustrate the interconnectedness of celestial bodies. Even a transient visitor leaves a fingerprint on the systems it crosses. The energy transfer is minute, but the principle is absolute. Nothing passes through the universe untouched. In laboratories on Earth, researchers continued to analyze the spectral data captured during those few months of visibility. Using refined models, they reconstructed not just the composition, but the likely thermal history of its materials. Certain spectral lines suggested the presence of hydrated silicates, minerals that form only when liquid water interacts with rock. That discovery implied that the parent world of 3I Atlas once possessed warmth enough for liquid water to exist, perhaps fleetingly. It might have been a small moon orbiting a larger body, or a fragment of a dwarf planet where geothermal heat melted ice within. This possibility bridged an emotional distance between the object and humanity. The thought that water, even alien water, once flowed across the body that now wandered between the stars gave it a whisper of familiarity. The origin of such water became another avenue of speculation. In the early history of planetary systems, volatile compounds condense in the colder regions of protoplanetary disks. If 3I Atlas came from such a region, it could reveal how chemistry unfolds around stars of different types. By comparing its inferred isotopic composition to that of known comets, scientists could test whether the ratios of deuterium to hydrogen were universal or varied by stellar environment. The slight anomalies in its readings suggested that its star had a lower metallicity than the Sun, meaning it was older, forged from less enriched material. In a sense, the object carried within it a sample of a more ancient epoch of the galaxy, a relic from a time when fewer heavy elements existed. To study it was to look backward into the early chemical stages of the Milky Way. The recognition that 3I Atlas might be a piece of an ancient, possibly water-bearing body reframed the way scientists viewed the galaxy's potential for habitability. If fragments of such worlds are continuously exchanged between stars, then the ingredients for life are perpetually redistributed. Planets need not develop in isolation. They inherit and share material through the traffic of interstellar debris. Over billions of years, this process could create a galactic network of organic matter, a slow diffusion of potential across the cosmos. Life, then, might not be an isolated miracle, but an emergent property of continuous exchange. In this vision, 3I Atlas is both participant and proof, a messenger from another cradle of possibility. Even the smallest structural detail held implications for understanding these exchanges. Its albedo, the measure of its reflectivity, was lower than most solar system comets, suggesting a surface coated with complex organic residues. These carbon-rich polymers, often called tholins, are known to form under ultraviolet radiation acting on simple molecules like methane and nitrogen. Over millions of years, radiation darkens and hardens them into a tar-like crust. This coating acts as insulation, preventing deeper ices from evaporating quickly and allowing the body to survive multiple stellar encounters. It also implies that 3I Atlas has spent immense time exposed to cosmic radiation, accumulating an organic veneer that serves as both armor and archive. If life's chemistry were to arise anywhere, such compounds could serve as the first scaffolds, stable, complex, and universally distributed. The journey of 3I Atlas also illuminated the fragility of observation itself. Its brightness curve was measurable for only a short time before fading beyond detection. The window through which humanity could study it was like a narrow crack between darknesses, brief, finite, precious. Astronomers have long dealt with transients, but never had the impermanence of data felt so palpable. Each photon gathered during its approach was irreplaceable, each second of exposure a unique chance to capture something that would never repeat. The object taught, perhaps unintentionally, a lesson about awareness, that even the most enduring cosmic entities exist to us only in moments. The light that revealed them is already gone. Still, the influence of that light persisted in imagination. Artists and thinkers across cultures found themselves drawn to the idea of a wanderer from another sun. It entered poetry, music, and speculative fiction, becoming a symbol of exile and continuity. For many, it represented the possibility of communication beyond language, a message not written in words but in motion, geometry, and chemistry. The shape of its orbit became a metaphor for fate, an arc that touches briefly and departs, leaving the observer changed. Even those uninterested in science sensed something profound in its visit, a quiet echo of universality that transcended data. Among scientists, its legacy expanded into practical innovation. Engineering teams began developing concepts for autonomous interceptors, spacecraft capable of launching from Earth orbit and accelerating toward newly discovered interstellar objects within weeks of detection. The challenge lay not in speed alone, but in readiness. To catch such an object requires not only propulsion, but predictive intelligence, software that can model trajectories in real time and adapt to evolving data. The blueprint of 3I Atlas's orbit became a training scenario for these systems, the first rehearsal for missions yet unflown. The hope was that the next visitor would not merely be observed, but met. That technological ambition reflects a deeper philosophical impulse, the human desire not to let knowledge slip away unrecorded. 3. I-Atlas had passed too swiftly for direct contact, but its absence ignited determination. Scientists realized that the universe often offers chances only once, and readiness transforms coincidence into discovery. In preparing for future interstellar encounters, humanity acknowledges its growing role as an active participant in galactic history. The observers are becoming explorers, the passive watchers turning into architects of contact. The silent passage of one object has redefined what vigilance means on a cosmic scale. Meanwhile, the study of its faint dust trail within the solar system produced unexpected results. Sensitive detectors aboard outer planet missions picked up particles whose composition matched predictions for the debris of 3I Atlas. These microscopic grains, likely stripped from the object by solar radiation, now drifted through the system at high velocity. Some eventually entered Earth's atmosphere, burning as meteors invisible to the naked eye. In this way, atoms from another world became momentary streaks of light across our sky. Even without direct interception, the solar system had absorbed part of its visitor, incorporating it into its own eternal dust. The realization that such exchanges occur naturally added a layer of intimacy to cosmic processes. Every time a meteor falls, it might contain atoms that have traveled between stars. The atmosphere, the oceans, the rocks beneath human feet may already hold material that began elsewhere. 3. I-Atlas merely made that process visible. It reminded humanity that the boundaries between systems are permeable, that the galaxy is less a collection of isolated worlds and more a single body in perpetual circulation. To contemplate that circulation is to glimpse the continuity that binds creation itself, a continuum where every atom is both ancient and itinerant. The idea of interstellar dust integration carries scientific weight as well. When such particles enter planetary atmospheres, they deliver trace elements that can influence chemistry on global scales. In the early Earth, similar infall may have provided organic molecules that seeded prebiotic reactions. By modeling the flux of material from interstellar sources like 3I Atlas, scientists can estimate how frequently these deliveries occur. The numbers suggest that Earth, and likely countless other worlds, receives measurable quantities of foreign matter every millennium. Over geological timescales, that steady drizzle of alien dust becomes significant, a quiet cosmic exchange that may have helped ignite the chemistry of life itself. From another perspective, the endurance of 3I Atlas highlights the stability of galactic motion. The object's trajectory through the Milky Way will follow predictable arcs around the galactic center, oscillating above and below the plane of the disk as it travels. In each oscillation, it will encounter regions of differing density, clouds, voids, and the faint pull of passing stars. These interactions may subtly reshape its orbit, but its fundamental journey will persist for hundreds of millions of years. It is a traveler not just through space, but through the evolving structure of the galaxy. When future astronomers model the Milky Way's dynamic history, such objects become markers, natural probes that trace gravitational patterns across epochs. If one could see its path drawn across cosmic time, it would resemble a thread weaving through the spiral arms, looping with the galaxy's rotation. Each loop corresponds to one galactic year, about 200 million Earth years. In that sense, 3I Atlas will complete many such revolutions while the stars themselves drift and die. The thought of this silent persistence evokes awe. While civilizations rise and vanish, it will continue its endless orbit around the galactic heart, indifferent yet faithful to the mathematics of gravity. The deeper mystery, however, lies in the process that launched it. Somewhere long ago, a gravitational interaction, perhaps between a giant planet and a smaller body, flung it outward with enough speed to escape its star's grasp. The precision required for such ejection is delicate. Too little momentum, and the object would fall back. Too much, and it would shatter. The fact that 3I Atlas survived intact speaks to the subtle harmony of forces that shaped it. It is a product of violence that achieved equilibrium, a relic of catastrophe that found peace in motion. This paradox, stability born of chaos, echoes throughout the cosmos. Every star, planet, and comet exists because of collisions and collapses. Creation is never gentle, yet it gives rise to serenity. Imagining that original ejection invites speculation about the world it left behind. Perhaps that system still exists, circling a star unseen from Earth, its planets orbiting in silence, unaware that one of their ancient fragments is now a legend among another species. If those worlds harbor observers, they might see their lost object one day through their own telescopes and call it by another name. They might even trace its path and realize that it once visited a yellow star halfway across the galaxy. The thought creates a poetic symmetry: two civilizations, separated by light years, connected by a single drifting stone. In this vision, 3I Atlas becomes not only a scientific phenomenon, but a bridge across time and intelligence. It embodies communication without intent, the exchange of existence itself. It reminds any who notice it that the universe is woven together not by sound or signal, but by motion and matter. The journey of a single fragment can connect species that never meet, eras that never overlap. This silent dialogue, unspoken yet undeniable, may be the most fundamental form of cosmic communication. Meanwhile, back within the human realm, its influence continues subtly. Educational programs use its story to inspire curiosity about physics, chemistry, and the nature of exploration. It becomes a gateway into understanding how small observations can reveal immense truths. Students learning about it come to see the universe not as distant spectacle, but as a living process in which Earth itself participates. The simple act of detecting a faint object across the sky transforms into an experience of belonging, a realization that even our smallest instruments are extensions of the cosmos trying to understand itself. From a technological viewpoint, the legacy of 3I Atlas may extend even further. The data it inspired have informed designs for new spectrometers, optimized for rapid characterization of faint moving targets. It also spurred advancements in global data sharing, as observatories around the world coordinated in near real time. This cooperation laid the groundwork for future systems capable of monitoring the entire sky continuously, ensuring that no interstellar visitor goes unnoticed. Thus, a single detection catalyzed a new infrastructure for planetary and interstellar science alike. Its impact, though born of a brief encounter, will ripple through generations of research. In a more reflective sense, the phenomenon rekindled discussion about humanity's own impermanence. Observing an object that has existed for billions of years forces confrontation with the brevity of human lifespans and civilizations. Yet, rather than induce despair, this awareness often yields perspective. The fact that we can comprehend and record such immense timescales is itself a triumph of consciousness. It proves that the universe, through us, has developed a means of knowing itself. When telescopes tracked 3I Atlas, the photons bouncing off its surface completed a journey begun in another star's nursery. Their detection closed a circuit of awareness stretching across space and time. For an instant, the galaxy looked back at itself. The thought of that exchange lingers. Somewhere far ahead in its path, the object will enter regions where interstellar gas becomes denser, remnants of old supernova shells or the edges of forming molecular clouds. There, its passage will stir faint electromagnetic wakes, tiny disturbances detectable only in theory. These interactions, though imperceptible to humans, are part of the ongoing conversation of the galaxy. Each moving mass, each charged particle contributes to the collective rhythm of the cosmos. 3. Atlas is both participant and instrument in that symphony, playing its silent note on a scale of millions of years. In that vast continuity, one might wonder whether such objects ever end their wandering. Gravity, subtle and patient, ensures that many will eventually be captured again. Perhaps in some far-off epoch, 3I Atlas will drift close to another star and become part of a new planetary system. There it may collide with a larger body, melt into magma, and rejoin the cycle of planetary formation. In that sense, its journey is not endless but circular. It will become material for new worlds, its atoms reorganized into mountains, oceans, or perhaps living organisms. What we saw as departure may be only the beginning of its transformation. The universe wastes nothing. Even the most solitary traveler will one day find a home. Such speculation stretches imagination to its limits, yet it harmonizes with everything known about cosmic evolution. The same processes that govern stars and planets govern this fragment. Its story mirrors the greater narrative of matter: condensation, disruption, motion, and renewal. The difference is scale, not substance. To see that connection is to sense the unity underlying all phenomena. The path of 3I Atlas is our own, written in another language of orbit and inertia. Its endurance through the void mirrors the endurance of life against entropy. Both are expressions of persistence in a universe that tends toward dispersal. In the centuries to come, as memory of its passage becomes historical record, humanity may evolve beyond Earth, sending its own vessels into interstellar space. Those emissaries will follow trajectories not unlike 3I Atlas, coasting through darkness toward unknown stars. In them, our species will echo the natural motion of such objects, repeating the pattern with intent. Perhaps one day, far from the solar system, a human-made probe will pass within view of 3I Atlas itself, both travelers drifting in opposite directions, one born of intelligence, the other of accident. Their meeting, if it ever occurs, will be invisible, but the symbolism would be profound. Nature and consciousness intersecting in the middle distance of the galaxy. Until that distant moment, the object remains what it has always been, a patient witness to the unfolding of the cosmos. It drifts beyond the influence of any single star, carrying within it the quiet testimony of countless cycles. Its surface darkens further with each passing millennium. Its internal chemistry stabilizes into deeper stillness, yet motion continues, steady, eternal, and unhurried. In every sense, it is the embodiment of cosmic persistence, the reminder that movement itself is the universe's only constant. And still, somewhere in that infinite distance ahead, light from a new star waits to touch it, another sun whose warmth will one day awaken its frozen ices. When that moment comes, millions or billions of years from now, the cycle will begin again. Sublimation, brightness, a brief tail of dust. New observers, wherever they exist, will look up and wonder at a stranger entering their skies. They will measure its, and those future observers will measure its light, trace its curve across their heavens, and find in its path the same questions that we once asked beneath our own sun. They will not know that their visitor has already been seen before, has already told its story once to another kind of mind orbiting another star. Yet the data they gather will mirror our own, differing only in detail but sharing the same essence, the same mystery. In this way, 3I Atlas will become an echo across civilizations, each discovery a verse in a poem written across time rather than space. Its meaning will not lie in any single observation, but in the continuity of wonder that follows it from one world to the next. The starlight that strikes it in that distant epoch will have changed, both in wavelength and intensity, filtered by the chemistry of another star's emission lines. That new radiation will awaken parts of its structure that remained dormant since its encounter with our sun, perhaps igniting volatile layers buried deep within its body. When heat seeps inward once more, pressure will build between strata of ancient ice and rock. Some of those pockets may burst, releasing gas and dust in arcs that spin away into the surrounding void. Each burst will sculpt the object further, chipping away at the features we once glimpsed, replacing them with others. Over time, the body will evolve again, remade by the environment it crosses. It will never truly be the same object twice. It will always be in the process of becoming. Even now, as it travels outward from our system, such transformations continue invisibly. The galactic environment is not static. Micrometeoroids, radiation, and magnetic fields are constantly reshaping its surface chemistry. The very color we recorded, those subtle reds and browns indicative of organic residues, will deepen as cosmic rays rearrange molecular bonds. Over eons, such radiation creates a polymeric crust so dense that it resists erosion almost indefinitely. That crust becomes both shield and record. Beneath it lies frozen history, protected until the next stellar encounter. Every layer, every alteration is a word in an unspoken language. The grammar of endurance written in elements instead of ink. If we could send a probe to follow it, equipped with instruments sensitive enough to map the changing magnetic and chemical environment it passes through, we would witness the long conversation between object and cosmos. The dust it meets, the plasma it crosses, the slow bending of its trajectory under distant gravitational tides, all these interactions form part of the invisible architecture of the Milky Way. Each drifting body like 3I Atlas is a probe launched by nature itself, gathering data not for us but for the galaxy's own equilibrium. We, by observing them, are reading the measurements already taken by the universe. Long after its departure, astrophysicists continued to refine the models that described its motion. They discovered that its outbound path took it not through a random direction but toward a region of relatively high stellar density near the galactic plane. In that future, it will likely pass within a few light-years of another star system, close enough for its trajectory to bend slightly once again. That gentle deflection will determine the next chapter of its odyssey. It might continue outward into the halo, the sparse outskirts of the Milky Way, or dive back toward the core, where gravitational tides are stronger. Either path ensures encounters. The galaxy is too full of motion for stillness. There is always another force waiting to nudge it, another region to cross, another fraction of its identity to erode or remake. If we imagine time not as linear but cyclical, then 3I, Atlas's journey becomes an orbit through eternity. Though it may never return to the sun, its motion is part of the galactic rotation that carries us all. In a sense, we are still moving with it, bound by the same vast rotation around the galactic center. The difference lies only in scale. Our revolution takes hundreds of millions of years, its own path perhaps billions. Yet both belong to the same dance. The object may have left our neighborhood, but not our galaxy's heartbeat. It shares the same gravitational rhythm, the same spiral pulse that shapes every star and world within the Milky Way. To contemplate that shared motion is to glimpse the interconnectedness of existence. The galaxies themselves drift through space in groups, those groups within clusters, those clusters within filaments. No particle or planet is truly alone. 3I Atlas may seem solitary, but its journey is threaded into this grand cosmic tapestry. Its velocity, its vector, its slow spin, all are responses to forces that stretch across millions of light years. It is both an individual and a participant in the choreography of creation. The concept of isolation dissolves when seen through such a lens. Even the loneliest traveler carries the imprint of everything it has ever touched. This awareness reshaped human understanding of what interstellar means. Once that term evoked emptiness, an expanse of nothingness between suns. Now it evokes continuity, the invisible highways of matter that connect systems together. Every grain of dust, every atom of carbon in the galaxy is in transit, exchanging hosts as it moves through cosmic time. Planets form, erode, and release fragments. Stars explode and seed the void with heavy elements. Comets carry those elements across light years. 3I Atlas is a node in that vast network of exchange, and its passage through our system was simply one visible node among countless unseen ones. The galaxy breathes through such exchanges, and we witnessed one inhalation, one exhalation in that rhythm. The psychological resonance of that vision is profound. It shifts perspective from human-centered curiosity to cosmic humility. To know that every molecule on Earth has likely crossed between stars before becoming part of us is to understand life itself as a continuation of galactic evolution. 3. Atlas, in this sense, is kin to the water in our veins and the silicon in our devices. Its matter and ours were both born from the same cycles of fusion and dispersal. Its journey, though different in form, mirrors our own collective motion through time. We too are travelers, short-lived but aware temporary constellations of matter that one day will drift apart and rejoin the endless flow. Scientists studying the dynamics of interstellar populations began to classify such objects not as anomalies, but as inevitable features of galactic ecosystems. They theorized the existence of streams, currents of interstellar bodies moving together along similar trajectories, relics of ancient disruptions. 3I Atlas might be part of such a stream, one fragment among many expelled from the same source millions of years ago. Somewhere out there, invisible in the dark, its siblings travel along parallel paths. Some may have already passed through other star systems, some may still be on approach to ours, and others may remain unseen forever. The notion that multiple fragments share a common origin adds richness to its story. It is not a solitary pilgrim, but part of a family dispersed by cosmic forces, still bound by the shared momentum of their birth. This idea led to a fascinating hypothesis. If these streams can be mapped, they could serve as tracers for reconstructing the history of stellar events. Each stream would point back toward a specific region of space, a site of planetary formation or destruction. By tracking the motions of such objects, astronomers could identify where stars once hosted complex systems and where gravitational upheavals tore them apart. In this way, the interstellar wanderers become messengers of memory, preserving evidence of systems long vanished. Their trajectories are like fossils of motion, recording not bones or shells, but the dynamics of creation and loss. In a quiet irony, the further 3I Atlas travels from any star, the more timeless it becomes. Bound to no orbit, unaffected by atmospheric friction or geological upheaval, it exists in a state close to immortality. Time for it flows differently, not in days or years, but in rotations, precessions, and encounters spaced by millions of seasons. Its changes are so gradual that to perceive them would require patience beyond human capacity. In that vast slowness lies a form of perfection. It is what it is, moment after moment, with no hurry to become anything else. The human mind, restless and transient, can only glimpse that serenity through imagination. Yet there is also fragility hidden within that seeming eternity. Cosmic rays, micrometeorite impacts, and the stresses of thermal cycling will eventually erode it grain by grain. Given enough time, it could fracture into smaller pieces, each continuing its own journey. Even in dissolution, the pattern persists. The galaxy thrives on such continuity through transformation. The fragments will follow diverging paths, scattering like seeds from a cosmic tree. Each will carry within it the chemistry of the original body, the fingerprint of its parent star. Thus, even decay becomes a form of propagation. Nothing truly ends. It only multiplies into new beginnings. Within that framework, 3I Atlas serves as a metaphor for the resilience of information. Just as physical matter endures through transformation, so does knowledge. The data recorded about it, the spectra, the orbit, the models, are now stored in digital archives that may outlast civilizations. Even if humanity fades, those patterns of information might survive in some form, encoded in successors or rediscovered by future beings. They, too, might reconstruct what we once saw, translating it back into understanding. In that sense, the study of the object becomes an act of preservation, not of the thing itself, but of the awareness it inspired. Philosophers have often spoken of the universe as a form of memory, where nothing is lost but merely rearranged. 3I Atlas fits perfectly into that vision. It is both an artifact and a process, a moving record of cosmic memory continually rewritten by the environments it passes through. The hydrogen atoms in its ices remember the density of the nebula that birthed them. The carbon chains in its crust remember the radiation of ancient stars. The trajectory it follows remembers the gravitational impulses that set it free. In this view, to exist is to remember, and every motion is an act of recall. The universe tells its story through motion, and 3I Atlas is one of its storytellers. The metaphor extends naturally to human thought. When scientists model its trajectory, they engage in a mirror process, reconstructing the past through fragments of motion. The equations describing its path are not mere mathematics. They are the human mind's attempt to resonate with the same logic that shaped the object itself. The alignment between cognition and cosmos, between idea and reality, suggests that consciousness is not separate from the universe, but an emergent property of its coherence. We think because the universe moves in patterns that can be thought about. To trace the orbit of a wandering stone is, in some subtle way, to participate in the very order that governs it. This recognition brings a kind of unity between the observer and the observed. When telescopes followed 3I Atlas, photons that had traveled for minutes or hours struck detectors and were converted into electrical signals, then into data, then into comprehension. In that chain of transformation, the object and the mind studying it became parts of one system, a feedback loop of energy and understanding. The light that left its surface entered human awareness, altering our species' knowledge and imagination. That awareness, in turn, changed our actions. New missions planned, new instruments built, new questions asked. Through observation, the universe evolves itself, consciousness becoming another channel through which matter learns its own structure. Meanwhile, the physical sciences continue to extract subtler truths from its example. The distribution of its ejection velocity compared to that of known exoplanetary systems helps refine models of how planetary scattering occurs. Simulations show that when giant planets migrate inward or outward, they can expel smaller bodies into interstellar space at velocities matching that of 3I Atlas. This confirms that such ejections are not rare accidents but common byproducts of system evolution. every planetary system at some stage releases material into the galaxy. The space between stars is therefore not barren but filled with the detritus of creation. Each piece carries within it a signature of its birthplace, collectively forming a galactic archive accessible to any civilization capable of looking. On Earth, as data accumulated, patterns began to emerge. The light curve analysis revealed subtle fluctuations inconsistent with a perfectly rigid body. These variations suggested internal motion, perhaps loose aggregates shifting under rotation or trapped gases escaping in small bursts. This internal activity implies that even after billions of years, the object remains dynamically alive, responding to stimuli with minute adjustments. The boundary between inanimate and animate blurs when viewed on such scales. The processes that animate it are mechanical, yet they produce behavior, rotation, vibration, self-regulation, that echoes biological persistence. The same principles that allow a cell to maintain equilibrium also govern the survival of a wandering comet. Life, in this cosmic sense, is continuity against entropy, and 3I Atlas exemplifies that definition. Its influence reached beyond the sciences into existential thought. Writers began using it as a symbol for identity across change, how something can pass through environments, lose material, gain new layers, and yet remain itself. In that metaphor, the object stands for consciousness enduring through the flux of experience. Just as it carries traces of all its encounters, so do human beings carry memories of every place, every event that shaped them. The orbit becomes a psychological map, and the cosmos a mirror of inner movement. 3I Atlas thus occupies two domains at once, the physical and the mythic, bridging them with effortless coherence. As decades pass and it moves further from our reach, new technologies may still find ways to listen for its presence. Instruments sensitive to the faint polarization of scattered light could detect it long after it fades visually. Eventually, radio telescopes might pick up minute reflections from background emissions bouncing off its surface. Even at vast distances, its whisper remains, encoded in the faint modulations of interstellar noise. Each detection, no matter how small, would reaffirm its existence, keeping the thread of observation unbroken. The object becomes a distant punctuation in the ongoing sentence of human curiosity, a semicolon between what has been discovered and what is yet to come. When considering its eventual fate, one must also account for the slow evolution of the galaxy itself. Over billions of years, the Milky Way will merge with neighboring systems, its shape stretched and redefined. 3I Atlas will be carried along in that transformation, its orbit folded into new gravitational frameworks. Long after the sun is gone, swollen into a red giant and then a white dwarf, the object will persist, gliding through a galaxy remade by time. It may pass through regions where new stars are forming, where dust coalesces into planets, where new eyes will one day look outward. In those moments, its meaning will renew itself. The story we began will continue, translated into other contexts, other languages of understanding. It is tempting to imagine what those future minds might think when they detect it. Will they see it as an ordinary comet? Or will they recognize it as an interstellar messenger? Will they wonder, as we did, whether it carries complex organics, whether it once passed close to another sun? Perhaps their own science will allow them to read its isotopic record directly, decoding its history with precision we can only dream of. They may even trace its past encounters, reconstructing that brief passage through the solar system of a long-vanished civilization. In doing so, they would be reading us, too, our telescopes, our curiosity, our fleeting awareness, inscribed invisibly within its trajectory. Far beyond the reach of any planetary orbit, 3I Atlas drifts onward, gliding through a darkness that is not truly empty, but woven with filaments of energy, invisible fields, and traces of ancient starlight. The galaxy hums quietly around it. Even here, in a realm so cold and thin that one might imagine nothing could happen, there is constant dialogue between particles and forces. Charged ions spiral along magnetic lines. Photons from distant supernovae ripple through the dust. Waves of gravity whisper from events millions of years gone, passing through the body of the traveler like ripples through a stone submerged in the deepest ocean. 3I Atlas is no longer a comet in the common sense. It is a node, a listening post for the music of the cosmos. It carries no instruments, but its very matter vibrates subtly with these interactions. Each tremor writes another line in the physical history of the universe. The silence around it is deceptive. Silence in space is not absence, but equilibrium. A balance so perfect that motion occurs without sound or friction. The object's spin remains almost constant, a faint tumbling with a rhythm measured in hours, perhaps days. Over time, that spin changes imperceptibly, slowed by the faint drag of solar particles it still meets on the edge of the heliopause. When it finally leaves that region, its rotation will stabilize again, set to a pace that could persist for millions of years. The slow turning gives sunlight from distant stars the chance to paint every side of it equally, polishing one hemisphere as another cools. The result is a form of equilibrium that mimics breath, a slow inhalation of heat, a slow exhalation into the void. Even at its current distance, its surface remains dynamic on the molecular scale. Radiation interacts with trapped volatiles beneath the crust, splitting them into radicals that recombine in new forms. In this hidden chemistry, 3I Atlas evolves. It is not life, but it is not lifeless. It exists in a continuous state of transformation. Each particle that strikes it rearranges a fraction of its molecules, creating compounds that have never existed elsewhere. These reactions may be fleeting, lasting only seconds before freezing again, but in the aggregate, they are a form of chemical storytelling. The object writes itself across time, letter by letter, in bonds and fractures. As it moves deeper into interstellar space, the ambient radiation background shifts. Cosmic rays become the dominant sculptor, bombarding it with energy powerful enough to penetrate meters below its surface. The energy deposits slowly change the crystalline structure of its ice. Hydrogen molecules trapped for eons are freed and reabsorbed. Layers of material densify, forming a harder, more glass-like composition. If ever recovered in the far future, such a structure would reveal the history of its exposure, each depth corresponding to an age, each mineral variant to a region of space crossed. It would be a map, not of geography but of experience. Every atomic arrangement would carry the echo of where it had been. The vastness around it is beyond comprehension, yet it is not entirely devoid of company. Within a few light years, countless other small objects trace their own paths. Rogue planets, dust clouds, asteroids ejected from unseen systems. Occasionally, trajectories align closely enough that two travelers pass within millions of kilometers, a proximity trivial on cosmic scales but meaningful in concept. During such near meetings, the gravitational influence of each body exerts a minuscule tug on the other, altering their courses by fractions of a millimeter per second. These exchanges accumulate like gentle brushstrokes in the grand mural of galactic evolution. The paths of such wanderers form an unseen lattice of motion, connecting stars through shared debris rather than light. From humanity's distant vantage, the journey of 3I Atlas continues to inspire theory and imagination alike. Computer simulations recreate its voyage through the interstellar medium, modeling every potential encounter it might have in millions of years to come. Some models suggest it will drift into a region where a supernova once exploded, where the interstellar medium is rich with heavier elements. If it passes through such a cloud, atoms of iron, nickel, and oxygen could adhere to its surface, embedding traces of stellar death within its already complex composition. Over time, those accretions could form a mosaic of origins, material from its home system fused with the remnants of others, uniting multiple generations of stars within a single rock. To contemplate such layering is to see the galaxy itself condensed into one fragment, a capsule of stellar ancestry. There is a persistent fascination with imagining what lies within its core. Models suggest that beneath the irradiated crust lies material untouched since the earliest days of its formation. In that deep interior, the ratio of isotopes could differ from anything in the solar system, offering a direct glimpse into the chemistry of another star's protoplanetary disk. The pressure may have compacted the inner ice into exotic forms, perhaps phases of water that exist only under extreme conditions, or clathrate structures trapping noble gases in crystal cages. Within such lattices, atoms have been imprisoned for billions of years, waiting for warmth to release them. One day, when 3I Atlas crosses near another star, those cages will open, and the gases of one world will mingle with the light of another. If time could be accelerated, the object's future would appear as a sequence of awakenings. Every few 100 million years, it might encounter another stellar system. Each time, radiation and heat would stir its surface into brief activity, producing tails of vapor and dust. Then it would return to dormancy, carrying new layers of residue from each passage. Over eons, it would become a palimpsest of systems, the physical embodiment of cosmic recurrence. To an observer capable of perceiving these vast timescales, it would resemble a spark that flares briefly and fades, only to reignite elsewhere, always changing yet always itself. The persistence of such an object reshapes our idea of mortality. Humanity tends to view permanence as a property of the monumental, mountains, planets, stars, but in truth, endurance belongs to the small and unassuming. A comet-sized fragment like 3I Atlas can outlive stars, can traverse epochs without losing its essence. Its survival depends not on mass or might, but on balance. Neither too volatile to disintegrate, nor too inert to lose energy entirely. It occupies the perfect middle ground between motion and stability. In that balance lies a metaphor for all things that endure, not resistance, but harmony with the forces that act upon them. Within theoretical astrophysics, objects like 3I Atlas are now considered keys to understanding galactic exchange. When a star system ejects such material, it also releases trace gases, magnetic fields, and cosmic dust. Over time, these contribute to the metallicity of interstellar space, enriching it for future generations of stars. The presence of interstellar comets thus ensures a continual renewal of raw material. The galaxy does not age in the way a living organism does. It recycles itself endlessly through such exchanges. Every object, no matter how small, participates in that rejuvenation. Even decay becomes a contribution. For humanity, observing 3I Atlas was a rare moment of communion with that process. It reminded the species that its own planet was once part of the same cycle, that Earth itself formed from interstellar debris enriched by ancient collisions. The object's visit was not an alien intrusion, but a homecoming of matter that once belonged to the same molecular clouds that birthed the sun. The difference lay only in trajectory. What we call foreign may simply be familiar matter traveling under another flag of gravity. Recognizing this erases a boundary. It makes every encounter with the cosmos an encounter with another version of ourselves. Philosophically, 3I Atlas also challenges the notion of purpose. It travels without intent, yet its existence generates meaning. The significance we ascribe to it arises not from any mission it undertakes, but from the curiosity it provokes. This dynamic mirrors the broader relationship between humanity and the cosmos. The universe does not strive to communicate, yet by observing it, we create communication. The act of perception itself is a bridge between randomness and understanding. 3I Atlas thus becomes a mirror in which we see both the indifference of nature and the capacity of consciousness to draw order from it. Within the inner layers of its surface, cosmic radiation continuously produces isotopes, short-lived elements that decay over predictable timescales. If one could sample them, their ratios would reveal the exact duration of its exposure to different regions of radiation intensity. This natural clock could allow future scientists to reconstruct its path with astonishing accuracy. The body itself is a chronometer recording the pulse of time in nuclear signatures. Each isotope decays, but together they form a continuous record, as if the object carries its own biography encoded in atoms. The universe gives every traveler a memory, even those without minds. Beyond the realm of scientific analysis, 3I Atlas also occupies a growing role in cultural mythology. To poets and thinkers, it represents solitude without despair, emotion that continues even without witness. The image of an interstellar traveler, indifferent yet enduring, becomes a metaphor for perseverance amid the unknown. In art and literature, it stands for the human condition projected onto the scale of the cosmos, to move through darkness, guided by the faint reflection of distant light. Its lack of destination becomes a form of freedom, its endless motion an act of faith in the continuity of being. The implications of its discovery ripple further into the concept of communication itself. If interstellar debris can move between stars, so too could deliberate messages encoded within such objects. Scientists have speculated that civilizations might one day use naturally occurring interstellar visitors as carriers for information, embedding microscopic archives within their structures, allowing them to drift for millennia until intercepted. While 3I Atlas carries no such payload, its existence makes the concept tangible. The galaxy already provides the delivery system. Intelligence need only add intention. In this vision, the cosmos could one day become a network of silent couriers, each carrying the memory of countless cultures across the dark. From the perspective of energy, 3I Atlas is a reservoir of potential waiting to be awakened. Its frozen gases store chemical energy equivalent to billions of tons of fuel. Should a future civilization encounter it, they might mine it as a source of hydrogen or organic compounds. In that way, it could one day contribute directly to the spread of life or technology across the stars. Even now, as an inert traveler, it holds within it the possibility of transformation. It may become a resource, a research object, or simply a marker of the galaxy's vast interconnection. Its value transcends utility. It exists as potential itself. The patterns of dust that once surrounded it have now diffused into the solar system's outer regions, blending with native particles. Each grain reflects sunlight faintly, contributing to the diffuse glow that astronomers call the zodiacal light. Thus, even though the main body has departed, fragments of it continue to shimmer in our night skies, unseen but present. The visitor has left traces behind, weaving its existence into ours in a quiet, enduring way. Every photon of scattered light that reaches human eyes carries a microscopic piece of its memory. If one could look back from its current location, the sun would appear as a tiny star among billions, indistinguishable from the background except to one who remembers its warmth. That memory, however, is written in motion. The slight increase in spin speed, the residual loss of mass, the new composition of the crust. These changes are the physical manifestation of having passed near a star. The object carries the evidence of that encounter like a scar, one that will never fade completely. Long after it leaves our galactic neighborhood, the subtle alterations will testify to the brief moment it once glowed under a foreign sun. As the centuries turn, humanity may evolve beyond the planet that first saw it. Colonies on moons and asteroids will look back at the records of 3I Atlas and see in it an early symbol of the interstellar age. The idea that an unpiloted piece of rock could cross between stars will inspire the construction of vessels designed to do the same by choice. When the first human-made probes leave the solar system in earnest, they will follow the example set by this natural traveler. Its path will have been both precursor and invitation. The notion of motion without return, once purely poetic, will become a blueprint for exploration. Even if no civilization ever meets it again, 3I Atlas will continue to influence thought indirectly. The equations derived from its motion will remain embedded in astrophysical models, shaping predictions for how other interstellar bodies behave. Each new discovery will be compared against its precedent. In that sense, it achieves a kind of immortality within knowledge itself. Just as fossils guide the study of life long after the creatures that made them have vanished, 3I Atlas guides the study of interstellar matter long after it has left our sight. The name may fade, but the framework it inspired will endure. One of the most profound realizations that emerged from its study concerns scale. When humans measure something that has traveled for millions of years, they confront the vastness of duration directly. The numbers, distances in astronomical units, velocities in kilometers per second, are abstractions until one realizes that each represents an unbroken chain of motion lasting longer than any history known to humankind. 3I Atlas becomes a bridge between human temporality and cosmic time, forcing the mind to stretch beyond comfort. To understand it fully requires imagining persistence without end, motion without destination, change without loss. Such imagination is itself an act of transformation, expanding awareness toward the scale of the universe. The object's continued journey also reshapes the question of origin. We often think of beginnings as fixed points, but in the cosmic sense, beginnings are distributed. The particles that compose 3I Atlas may have originated in several different stars before coalescing into its parent world. Its creation is thus a collaboration between multiple stellar histories, each contributing its own materials and energies. The concept of individuality loses meaning under such conditions. Everything that exists is a mosaic assembled from prior existences. 3I Atlas is not a single story, but a convergence of countless others united for a time under one gravitational form. There is beauty in this realization. It suggests that nothing in the universe is ever truly separate. Stars, planets, comets, living beings, All are permutations of the same ancient matter, continually reshaped by motion. The galaxy is not a collection of isolated entities, but a flowing continuum of transformation. 3. Atlas embodies that truth with silent eloquence. It moves through the darkness not as an intruder, but as a participant in the perpetual circulation of existence. Each encounter, each alteration renews its membership in the cosmos, and still it travels, beyond the realm of our instruments, beyond the boundary where human imagination begins to blur into wonder. Somewhere ahead lies another region of dust, another gravitational current, another chance for transformation. It will continue to drift until drawn again toward the warmth of a star, where for a brief instant it will blaze once more, its frozen memories released into light and motion. Another world will see it then, another intelligence perhaps, or none at all, only starlight reflecting on ancient ice, continuing the story we began but could never finish. The journey has no conclusion, only continuations, and 3i Atlas moves toward them still, unhurried, bearing the unspoken promise of everything yet to be told. Beyond the outermost traces of solar wind, where the heliopause dissolves into the vast and undefined ocean of interstellar space, 3i Atlas continues its measured drift. Its course is so constant that, if one could superimpose the lines of its motion onto a map of the Milky Way, it would appear almost like a pulse, steady, indifferent, eternal. The faint influence of the sun has faded entirely now. It is guided only by the gravitational murmurs of unseen stars and the slow undulation of galactic tides. The object, cold beyond imagination, spins lazily as it travels, presenting every facet of itself to the faint starlight that reaches across unimaginable distances. What little light touches its surface is scattered like whispers through a cathedral built of emptiness. The silence that surrounds it is the kind that only exists where distance is infinite and time has no rhythm. Yet silence is never stillness. In the dustless dark between stars, stray hydrogen atoms float singly, and the interstellar magnetic field twists them into currents as faint as dreams. These imperceptible threads of force tug at 3i Atlas as it passes, changing its course by distances measured in molecules. Each alteration, however small, will one day determine where and when it meets the light of another sun. Even in isolation, it is part of a pattern too immense to perceive, like a leaf carried by a river whose current encircles the galaxy. Cosmic rays continue to strike it from every direction. They are relics of stellar explosions, particles hurled outward at nearly the speed of light. When they meet the body of 3i Atlas, they fracture molecules and create new isotopes, chipping away infinitesimal layers of matter. Over epochs, these impacts carve the faintest of pockmarks into its surface, leaving a topography visible only at microscopic scales. The crust, once a simple mantle of frozen organics and silicate dust, is transformed into something more complex, harder, darker, chemically richer. It becomes an armor of evolution by radiation, a record of endurance written one collision at a time. Deep inside, the story is different. The internal temperature is near absolute zero. Yet the pressure of ancient ice still bears down upon pockets of trapped gas. These sealed chambers, relics of formation, may have held their contents for hundreds of millions of years. Inside them, molecules are preserved as if time itself had paused. If some future explorer could ever drill into that core, they would find an archive of cosmic infancy, frozen compounds unaltered since the dawn of its parent system. Methane, ammonia, carbon dioxide. These ordinary substances are pieces of an ancient language, each element a syllable in the grammar of worlds long extinguished. Though 3i Atlas is silent, the galaxy speaks around it. Radio waves from pulsars, each spinning neutron star a cosmic metronome, pass through its vicinity. These signals, regular as heartbeats, trace the structure of space-time itself. They ripple through the material of 3i Atlas, producing vibrations far too faint to be detected, yet sufficient to shake dust grains into new configurations. Every photon, every wave, every field that touches it leaves an impression. It is not an inert object so much as a listener, recording the harmonics of existence through its own substance. Its path becomes a score, and the galaxy the orchestra performing it. Over millions of years, 3i Atlas will cross regions of varying density. There will be times when it enters the thin outskirts of a molecular cloud, a place where hydrogen atoms pair into molecules and the seeds of new stars are forming. In such an environment, frost will begin to settle on its exterior, layer upon layer of delicate crystalline coating. The surface, once rough and dark, will gleam faintly in the ultraviolet light of nearby protostars. These new ices will capture traces of the environment through which the object passes. Different isotopic signatures, different ratios of deuterium and oxygen. Each encounter thus writes another chapter in its physical autobiography, a slow accumulation of experience rendered in matter rather than memory. Occasionally, gravity will play its subtle hand. A distant star, passing within a light year or two, will curve space just enough to draw the object onto a slightly altered vector. The change will be imperceptible in the short term, but immense in consequence. Millions of years later, this tiny deflection may bring it into contact with another system rather than leaving it adrift in solitude. In the arithmetic of celestial mechanics, small influences compound into destiny. The future course of 3I Atlas is being rewritten continuously by such invisible negotiations. The scale of this journey defies comprehension. The galaxy is 100,000 light-years across, and yet this lone traveler will take perhaps half that distance in its slow orbit around the galactic core. It will cross through spiral arms thick with dust, through voids emptied by supernova winds, and through regions where starlight is filtered through veils of carbon molecules. Each of these domains will act upon it differently. In one era, it may gather frost. In another, it may be sandblasted clean by interstellar particles moving at tremendous speeds. There is no permanence except change, and even the shape of 3I Atlas will shift slightly with every passage through these varying environments. To imagine this journey is to confront time on a scale beyond any human reference. Whole civilizations could rise and vanish in the span of a single degree of its rotation around the galactic center. Empires, species, perhaps entire biospheres may appear and disappear on distant worlds, unnoticed by the traveler that glides silently past. Yet its presence, unobserved though it may be, will still influence the gravitational balance of the stars it passes. The universe, vast as it is, never forgets a visitor. Even the faintest body alters the equations that describe its motion. Every particle of 3I Atlas participates in that unending dialogue of force and reaction. If one could follow the path backward through time, the story would eventually return to the moment of ejection from its home system. There, perhaps, a giant planet's migration disturbed the harmony of orbits, sending fragments outward like sparks from a grinding wheel. 3I Atlas might have been part of a cometary belt or a moon fractured by collision. Whatever the cause, the expulsion required an exquisite alignment of energies, enough velocity to escape the parent star, but not so much as to tear the body apart. The fact that it endured is testimony to balance, a lesson that even chaos can produce coherence under the right conditions. Its parent star, wherever it lies, may no longer exist. Stars that form planets sometimes die violently, scattering their children into the void. If that star has gone supernova, then 3I Atlas carries the memory of a system extinguished. The isotopes within its structure would bear the marks of that cataclysm, traces of heavier elements forged in the final explosion. Thus, even in its exile, it remains the remnant of a cosmic lineage, the last echo of a world erased. To touch it would be to hold the ashes of another sky. On Earth, long after its passage, the data recorded during its brief visit continue to reveal subtleties. Advances in computational modeling allow scientists to simulate the way sunlight scattered from its uneven surface. From these simulations, they deduce that its shape was likely irregular, perhaps elongated like a spindle or flattened like a disc. Such a configuration may have affected the way it accelerated as it left the sun's vicinity. Non-gravitational forces, jets of sublimating gas, even radiation pressure, could have produced the faint anomaly observed in its trajectory. In this sense, the object was not a perfect passive traveler. It interacted dynamically with its environment, responding to heat and light like a living organism reacting to stimuli. These details have far-reaching implications. They suggest that the physics governing small bodies is more nuanced than once believed. The same equations that predict planetary orbits must now account for minute thermal effects and structural complexities. Each refinement of those equations enhances our understanding of the broader galactic architecture. 3I Atlas, through its brief appearance, forced a recalibration of celestial mechanics itself. It became a silent teacher, reshaping knowledge by the simple fact of being measured. Beyond the technical and the poetic lies the metaphysical question of awareness. When we describe an object moving through interstellar space, we often imagine it as senseless matter, yet on a certain level, awareness might not be limited to biology. The universe perceives itself through interaction. Every photon that strikes another particle is a form of recognition. By that measure, 3I Atlas participates in awareness continuously. It encounters, reacts, transforms. Its existence is an active relation. Though it cannot know us, it is known through us, and in that mutual contact, both observer and observed are altered. The boundary between consciousness and cosmos grows thin in such reflections. Even now, in its vast solitude, it is not entirely without influence upon Earth. The tiny grains of dust it shed during its passage are still orbiting the sun, moving in diffuse streams that occasionally intersect our planet's atmosphere. Each grain, when it collides with air at tremendous speed, burns into a microscopic meteor. These events occur silently, unnoticed, yet they connect the planet to the traveler across the gulf of space. Every such speck of light in the upper atmosphere is a brief reminder that something from beyond the solar system touched our world. The evidence falls like invisible rain, blending with the ancient dust already woven into the planet's geology. If one were to trace its motion across millions of years, there would be moments when 3I Atlas passes near regions dense with stellar winds, where particles stream outward from clusters of hot young stars. In those regions, the bombardment would be intense enough to strip away entire layers of material. Each such encounter resets part of its surface, erasing older features and exposing new ones beneath. Thus, over eons, it is both fossil and newborn, continually recreating itself. When it emerges from those environments, it carries forward the chemistry of the region it has crossed, like a vessel transporting samples between laboratories scattered across the galaxy. In its wake, it leaves a trail of altered space, minute gravitational perturbations, electromagnetic ripples, even the faint scattering of photons, all mark its passage. These traces will eventually fade into the background noise, yet for a time they exist as signatures of its journey. If any civilization elsewhere had instruments of sufficient sensitivity, they could, in principle, detect those disturbances and reconstruct the object's course. The universe is transparent to persistence. Every action, no matter how small, leaves echoes waiting to be deciphered. 3. I Atlas, though silent and unseen, continues to write its existence into the fabric of reality. The question arises, what might eventually end its voyage? There are several possibilities. It might collide with another object, though the probability is vanishingly small. It might be captured by the gravity of a star it passes near, falling into a new orbit as a long-period comet around that alien sun. Or after eons, it might be drawn into a molecular cloud dense enough to slow it, embedding it within the material from which new planets will form. In that final scenario, it would cease to be a traveler and become the seed of another world. Its atoms, once scattered through the void, would melt into the core of a newborn planet, beginning the cycle again. The journey of matter never truly ends. It merely changes context. Such thoughts lead inevitably to comparisons with humanity itself. Every element of life on Earth originated from processes as ancient and dispersed as those that shaped 3I Atlas. Carbon, oxygen, nitrogen, all were forged in stars that lived and died long before the sun ignited. In a very literal sense, life is interstellar material organized temporarily into awareness. To watch an object like 3I Atlas drift past is to watch ourselves in another form. It is not alien, it is ancestral. The difference lies not in composition but in consciousness. The same dust that drifts between the stars breathes within us. The traveler's endurance is mirrored in our own desire to understand it. As it journeys through the galaxy's magnetic arms, the radiation environment will continue to sculpt its destiny. Particles moving near light speed can embed themselves in its surface, altering the local magnetism and perhaps creating faint electric currents when the object passes through varying magnetic fields. These currents might heat minute regions, causing localized sublimation or rearrangement of crystalline structures. Over enough time, the process could subtly shift its spin or orientation. In this way, even electromagnetic whispers become sculptors of fate. The universe leaves nothing untouched by its invisible hand. Imagine far in the future a distant civilization orbiting a red dwarf star. Their telescopes detect a small object entering their system, moving at extraordinary speed, its path hyperbolic and unmistakably interstellar. They track it, analyze its light, and find signatures of organic compounds, traces of hydrocarbons darkened by radiation. They name it anew, unaware that this same body once visited another system, circling a yellow star where beings of carbon and water once looked up and wondered about it. For them, too, it will be a mystery, a message written without a sender, a fragment of the universe wandering between its own questions. The cycle of wonder thus perpetuates itself. Every civilization that glimpses 3I Atlas will see its own reflection in it. The questions they ask, where did it come from? What forces shaped it? What secrets does it carry? Will be the same, echoing across epochs and light years. In that repetition lies the unity of intelligent life. The object becomes a shared reference point for curiosity, linking minds that will never meet, binding consciousness across time. It does not communicate in language but in presence, a form of communion older and broader than words. Perhaps the greatest lesson it offers is about perspective. On the scale of galaxies, even light is slow. Yet 3I Atlas moves patiently, obeying the mathematics of inertia. It teaches that motion does not require haste and that destiny unfolds at the speed of endurance. In its quiet trajectory, it embodies a kind of serenity unknown to worlds burdened by urgency. It reminds any who study it that existence is not a race toward an ending but a continuum of transformations. Every moment, however small, is a destination within the infinite journey, and still it travels onward. Its path extends into eras so distant that the shapes of constellations will have long since changed. Stars will have died and others been born in their place. The Milky Way itself will have drifted toward its eventual merger with another galaxy. Through all these shifts, 3I Atlas will remain in motion, carrying the same atoms that once shimmered under the light of our sun. When it passes through the new, merged galactic sea, it may once again find itself illuminated by unfamiliar constellations, its surface reflecting the glow of civilizations not yet imagined. Somewhere ahead, gravity waits to beckon it once more. Another system, another star, another world will cross its path, drawing it in with a silent invitation. The frozen gases will awaken again, the dust will rise in a luminous tail, and a new set of eyes will turn toward the sky in wonder, tracing the same trajectory that once graced our own. The cycle will continue, unbroken, and 3I Atlas will go on writing its endless story through light, motion, and the quiet persistence of time still unfolding beyond any horizon we can yet see. As it moves through the boundless dark, 3I Atlas drifts past tendrils of unseen plasma that hum with the residue of ancient stars. Each particle it encounters reshapes the electric skin of space around it, a faint shimmer of disturbance invisible to any eye. No sound follows, yet its motion composes an unending symphony between gravity and dust, an orchestration of chance and permanence. Far ahead, light from a yet unborn star travels outward to meet it, a meeting written long before either existed. In that destined intersection lies another beginning, another brief illumination before the darkness resumes its slow embrace. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on everything we know about 3I Atlas? We want to hear from you. Thank you for watching, and see you next time.